Dear ladies and gentlemen, welcome everyone to the second edition of Baltic Fire Forum. I greet you from Vilnius, the capital of Lithuania, Litexpo Trading Conference Center, our media center, our online temporary home for 2 days. I'm really glad to see so much already connected viewers, and I'm really amazed by the geography that expanded, from the first time when we'd done it 2 years ago. It was meant only for Baltic region, Baltic Sea region. Now we have a geographic from Spain to China, from Finland to Ukraine. So thank you very much. Thank you for this achievement. We couldn't do this without you. This time, no live trainings. We have no containers with fire and flames. We do not do any hot smoke tests. We do not shake our hands when we meet. But nevertheless, the quality of this event, even though we do it online, the quality is rising and rising. I'm really glad to see so much professors from universities, specialists from accredited laboratories who are joining with their presentations. And it's really amazing how fire engineering is advancing. It's some day ago it was quite a challenge. Now it's advancing every single day, and I'm very thankful that you are joining this event together with us. Every forum has kind of a mission. Our mission was chosen with very clear view. It's zero casualties caused by fire in Lithuania, zero casualties caused by fire in Latvia and Estonia. Is it possible? Yes, it is. Okay, not tomorrow or maybe not in 1 year, but you will ask, how can we achieve that? Having all the most modern technologies in the world. Smoke detection is so much advanced. Smoke exhaust, firefighting systems, all they are installed in the building, and still we have some casualties. Our firefighters are getting more and more effective. Why? Well, maybe that's a mindset. Mindset is always the thing that could be changed. Of course, it's not very much easy, but our mission and our goal is to reach it by 2025, when we once again meet in the Baltic Fire Forum. So changing the mindset in our engineering way, I think if we start by doing and feeling this social responsibility, which is not just the words. In our engineering world, the designing with responsibility means saving someone's lives. And I hope that Baltic Fire Forum will be this platform when firefighters and fire engineers can share this knowledge, and we can achieve this zero casualties goal. Thank you very much for joining me today, and I hope you will like it, this 2 days journey in fire safety engineering. Welcome and enjoy. Good morning, Simonas.
Good morning, Martinas.
Nice to meet you again.
Nice to meet you too.
Now it's the second edition already of the Baltic Fire Forum, and I'm actually really glad because we met at the first edition.
Yes.
Exactly two years ago.
Yeah.
How did you like it?
I remember very good that conference.
Uh-huh.
I was maybe for 1 day or 2 days.
Yeah.
So really, I'm thinking about that conference still nowadays.
So sorry, we cannot make it live. We do not do any flames, no smoke, and basically we do not make any trade fair this year due to COVID-19 virus situation. But nevertheless, the quality of the presentation will just go up and up and up. This is really good.
Absolutely.
So, Simonas, do you remember Szymon Kokot-Gura? He was one of the key and is today.
Yes, Szymon. I remember him perfect. Yeah, one of the best specialists in Europe. Yes. Shimon.
So I'm really glad once again to tell you that Shimon is the keynote speaker.
Oh,
Once again, we shall hear the presentations about tactical ventilation and using water as an extinguishing medium, just lots of sorts and
okay.
in different approaches. So I'm really looking forward to these presentations. Also, that Shimon is a dear friend of mine and a colleague, and it's from student times in Warsaw
Okay.
as GSP, the famous firefighting school. My question to you, Simonas, about the training in Lithuania. Uh, what is the organization which is making the instruction courses or training courses for firefighters?
Yeah,
Can you tell?
the main institution is like firefighters department of
Uh-huh.
Lithuania. Yeah, and one of the sections for training firefighters is firefighters training school. Yeah, so it's the main section for training. Everybody who wants to become a firefighter in Lithuania must to go there and yeah, learn.
Okay, this is nice. So, how long is it?
It takes 6 months.
Mhm.
Yeah, and that includes the basic drills, and the practice in the fire brigade, where you will be walking after finishing that school.
So after that, you are able just to start a job in a rescue team
Yes.
or national fire
Yeah, you
department.
became a professional
Okay.
firefighter.
Okay. What about the tactical ventilation? 2 years ago,
Mm.
we've also touched this
Yeah, I remember.
topic a
Yeah,
bit.
I remember.
Do we do anything here in Lithuania on the training ground?
Yeah, a little bit sad, but no, we just like know about that,
Hmm.
think about that, but not training, not using that system.
Okay. Okay.
Maybe it's the future. Yeah.
Yeah, good one. So then let me introduce you our keynote speaker, the firefighter tactical instructor from Olsztyn, Poland. And the topic is tactical ventilation during fire. Let's hear from you. So, Shimon, let's hear from you, and the stage is yours. Thank you very much.
Hello, everyone. My name is Szymon Kokot-Góra. I'm from Poland, and I have the privilege and honor to be presenting in front of you a couple of topics. So, first of all, I would like to introduce myself and tell you a little bit about myself, since I will be covering a couple of topics for you at the second Baltic Fire Forum conference. So we will move to my presentation now. And as I mentioned, I'm from Poland. I am a senior officer in the State Fire Service in the Republic of Poland. My current rank is major, which is equivalent to junior brigadier. I'm a master's in engineer in fire safety. I'm a occupational health and safety expert. I'm a qualified teacher and currently also a PhD candidate. And my main task is teaching about fire behavior in Poland. And currently I also coordinate the project of teaching instructors for structural firefighting in Poland. So this is my professional engagement. I'm also a deputy head of training center in Olsztyn. But today I'm speaking to you on behalf of my organization, which is called CFBT-PL. It's an abbreviation from a worldwide term, Compartment Fire Behavior Training, and as a representative of the Polish chapter, the Polish group, I'm connected with friends and colleagues from around the world, Europe, but also Asia or both Americas and so on, and we exchange ideas and try to make this profession as safe and as effective for us, for ourselves and for our customers, for the people whom we are helping, as much as possible. I also serve as a vice president of the Association of Fire Engineers and Technicians in my hometown. I was organizing the IFIW, the very prestigious workshop of international instructors in 2014, and was a participant in other years as well. And I also do motivational projects for firefighters. So yeah, this is me. I'm also starting to get used to this e-learning thing since we are in the COVID-19 era, so please bear with me. On this slide, you can see a little bit of my activity. We're trying to be very active with my colleagues in teaching, but also in learning, in international cooperation, and in many aspects of the job that are necessary. Some of them include firefighting, some of them include small skills, other are more tactical or strategic, but also we focus a lot on health. So you will have my colleague Alexander, who will speak to you also on cancer awareness for firefighters. And as I mentioned, even though I'm a teacher, I never stop to be a student. So here, and here you'll see also that I'm focused also on some other aspects of engaging people in teaching, empowering people and making them more interested and more enthusiastic about the profession. So this presentation covers rather a lengthy subject, so I decided to divide it in two parts, and it will focus on tactical ventilation. So we will have the ABC basically of tactical ventilation, since it's a very broad topic, and it takes a lot. It can take as long as 1 week of training as a consecutive stage of this topic. For example, after compartment fire behavior training, first part, second part, then tactical ventilation. For example, this is how it's done in the UK. So I'd like to make a small review, because this is basic firefighting knowledge about physics and chemistry of fire. Then I will try to show you how the concept of ventilation, and specifically air, was presented in history, how our predecessors already understood the importance of air for the fire. And then we will focus on tactical ventilation, which will include natural ventilation, something that is created by fire itself. We will also cover wind, which is a very important aspect in all of this. It's also a natural phenomena, but oftentimes it's very much underestimated. We will speak about isolation of fire, so it's also known under a term of anti-ventilation. And then we will speak also about hydraulic ventilation and forced ventilation, which has which has different also, which is realized in many different ways. So let's begin then. Enter search and flow path management, sorry, and also a little bit of tactical concepts such as ventilation, which is helping quick search, what is called snatch rescue, when a firefighter enters, grabs the victim and leaves the building. And also flow path management and the concept of 3T, to which I will get later. So I'll not go into details right now, since it's sort of something that is joining all the little elements that I will be presenting to you today. So it is quite common knowledge for every firefighter that the combustion process consists of 3 elements that, when put together, create the 4th element. So we have the fuel. It's basically everything that can burn, and there's a lot of things that can burn. Sometimes we even joke among firefighters that water burns because, hey, water is hydrogen and oxygen. Hydrogen is a highly combustible and explosive element that creates a crazy huge amount of heat, but it's not so easy to disconnect hydrogen from oxygen. So if it comes in the form of water, as it is in nature, and we have to remember water is older in space than our planet, then it's a very stable substance. So it's not so easy to disconnect hydrogen from oxygen and create an explosive mixture with pure oxygen. Then we have the oxidizer, which is a substance that has the ability to oxidize, which means to disconnect particles and bind them with particles of oxygen and create new chemical substances. Of course, in fires, we are talking about oxygen from the air. The air is present everywhere. So we have a fuel that is present everywhere, air that is present everywhere. And then we have heat. It's basically the heat, so the energy, because heat is energy, which we are expressing in joules. It's the heat that starts the fire, but also there's a necessary amount of heat to sustain the fire, to make the fire go without being extinguished. So obviously, as firefighters, we know that we want to either take away fuel or take away the oxygen or take away the heat, or some combination of those three in order to be able to stop the process. And then we have to remember that it's a chemical process. So in the presence of those three elements and from their interaction, there comes a fourth element, which is called free radicals. Free radicals are some mostly random compounds created during decomposition of materials, and they are characterized by having the free electron or unpaired electron, which makes them highly reactive, and they are responsible for the chain reaction of this process, which means that if we don't do anything to stop it, it will be sort of self-sustained. So, okay, when we have fire, then we have the problem, which is heat. Also smoke, but heat is the source of majority of problems when we are speaking about the mechanism, and the smoke is the effect of fire, which is also harmful, because we know that for population, inhalation with smoke, with toxic products of smoke, is the main cause of deaths in fires. But when we are talking about safety of firefighters, and that the firefighters are equipped with the self-contained breathing apparatus, with air packs, there is a duration of time they can work safely in a smoked atmosphere, but the problem is heat. Heat, because it's not only making effect on the firefighter, raising his body temperature and changing his physiology, but also it's acting on other fuels and then creating more free radicals and sustaining the chain reaction. But one of the important aspects that I would like to talk to you about is convection, because we have three ways of heat transfer. It's radiation by electromagnetic waves. So, for example, when the sun heats the planet, it doesn't need any mediary. It doesn't need any substance between to be able to send the energy. And it's coming from large distances and still reaching Earth, making the air or other items on air or other objects on air heated. And then conduction is something that is happening by the interaction of particles. The particles start to vibrate on a very small scale, and then they pass the vibration to another neighboring particle, and in such a way we have a conduction, which means that it's like the electricity going through the wire. So in the same manner, we have an object which is transferring heat. Of course, we know from examples, from experience, that some materials are very good conductors, like metal, and some are not so good conductors, like wood. So when we go to a barbecue or we go to a fire, we don't use metal sticks for making a sausage. We use rather wooden sticks, or at least have a wooden handle on our metal stick to make the sausage. But the thing is that there is a convection, which is by definition transfer of heat with mass, which means that unlike the solid material, the wood or the metal stick, as I mentioned before, the particles cannot move, so they vibrate. But in convection, which is happening in fluids are liquids and gases, so the substances that have the ability to mix their particles have internal movement. The convection is caused by differences of density. So when the density is becoming lower as the temperature rises, we have the natural, or we also call it gravitational, movement of mass of substance. And when this mass is moved, the heat contained in this mass, in those particles, is also moved. So convection is this kind of mechanism. Okay, then we also know that in order for gases to ignite, they have to have a proper concentration. We will take the example of methane gas, which is a hydrocarbon gas coming from nature, basically. And we know that only if there's enough substance in the mixture of air, or it's above the what is called lower explosive limit and below what is called upper explosive limit, which on this graphic are marked by 4.8% concentration and 14.8 concentration, 14.8% concentration. So in those boundaries, this gas can ignite and can combust. It's a very characteristic feature for every gas. So every gas will have a different concentration or limits, the lower and the upper explosive limit or flammability limit. We can use both names because explosion is a form of combustion as well. And we also have to remember that there's an ideal mixture, which is also characteristic for every substance. And in this ideal state, which is called stoichiometric concentration, there is oxygen for every particle of the substance, which means that sort of nothing gets wasted, everything gets combusted. And in this kind of mixture, we get most violent effects of combustion. Basically, what we are talking about here is the increase of pressure. I also have to add that we understand that heat is not a state. Heat is energy, but we understand the world around us more through the perspective of temperature. Temperature relates to heat in a way that if heat is energy, then temperature is a state that an object reaches by the effect of this energy. And of course, we can add certain amount of heat to different substances, and their temperature will depend on their characteristic as well. So it's not always linear and not always identical, or rather it's rather rarely identical for different substances. Okay, so we will be interested in the following effects of the combustion process. When we have combustion, there is smoke created. Smoke is a mixture of different states. It can have solids like soot. It can have liquids as well, but mainly we say it's a gaseous area or volume. In this volume, we have mostly gases, and gases are subject to natural laws. There are certain laws that apply to gases, even though we say there's a ideal gas equation, and we don't get ideal gases, and we have different concentrations of different kinds of gases of different chemical constitution, but still the general rule applies. On this graphic, you see a bottle with air, and it's used to explain the example of this Clapeyron equation or ideal gas equation. On the left side, we see PV, which is responds to pressure and volume, and on the right side we see N, R, and T. N is a mass in moles, mole mass, which is constant for a given mass of fuel. R is a gas constant, so another constant, and T is temperature. So if we make it simple, if we simplify this equation, we see that the pressure and volume are directly linked to temperature. And every firefighter will know that if you take a bottle of air for your SCBA, when you fill the bottle with air, it gets hot, because we see that P is rising, V is constant because it's the volume, the size of the bottle. So therefore T also has to rise. So we understand by this example that every time that either P or V or both are rising, the temperature is rising, and if they're decreasing, the temperature is decreasing. Or it can work the other way around. If we heat something, the pressure and volume expand, they grow, but if we cool something, it contracts, it takes smaller volume. So this thermal expansion is responsible for a number of behaviors of smoke. For example, the smoke will first of all rise. The effect is called buoyancy, which means it has the tendency to rise because its density is lower. So therefore we have hot air balloons. When we put a large fire inside the hot air balloon, it will fill up with the gas which is heated. It's lighter than air, and we will raise the balloon to the air, like in the famous story 80 around the world in 80 days. Okay. But also when we speak about gases, we have to understand that when we cool gases with water, to which I will go back in another presentation, the gases contract, they take less space. Another effect that is important for us is stack effect or chimney effect. We have to understand that the volume of gas, if it's heated, it's a volume that can move. If it moves, it acts like a piston in an engine. It either pushes or pulls something. So we have chimney effect. If the hot gases are being extracted in upper parts of a building, it will automatically create some under pressure in the lower parts. It's like a syringe. When we want to take water to a syringe, we pull the piston and we create under pressure, sort of like that, with the slight difference being that solids are not penetrable and gases they can flow. So basically it's not as a strong effect as in the syringe given by the example, but still this is something that is happening in fires. And then we have to understand that spread of fire is based in large part on pressures and flows. We have here on this drawing on the bottom 3 cases. Each of them will be presented separately in a large slide as well. So I will move to that and make my explanation of my point when I go there. We have to also remember that in order to understand fire, we have to be familiar with the basic model, the concept of the basic model. Here we see in the middle of the room, there's an armchair that is on fire. It has what we call the combustion zone or seat of fire. There's a flame. Over the flame, there's a convection zone, which means that in this zone, the fire gases, the heated gases travel upwards, and they travel upwards until they reach an obstacle. This obstacle inside the building is, of course, the ceiling. When it reaches the ceiling, it starts to spread to the sides. When it reaches another obstacle, which are the walls, it starts to build the smoke zone. So the depth or the distance of the smoke zone from the ceiling to the smoke-free zone is slightly rising. And of course, there's an interface which we call the neutral plane, which is a plane, or yes, like a platform between the smoke area and free from smoke area. And we have to understand also that there is radiation coming from both the seat of the fire, the flame itself, and also from hot gases, or even from the ceiling jet, which is a flame that grew so much that it cannot go upwards anymore because there's a ceiling and it starts to bend and it's traveling across the ceiling. So all these can become a source of radiation, and symbolically on the right side we see another armchair that is already decomposing, because in order to combust, any material has to become in a gaseous form. So gas is created. Sometimes it's the solid liquid gas, and sometimes it's only solid gas. So to give you an example, if we have a candle, the wax will first melt and become a liquid, and then it will vaporize and become a gas that can ignite and burn. But when we have a wood, it's not melting because it doesn't have the ability to melt, and it doesn't exist in a liquid state. It can only be a solid, and when we burn it, it becomes gas. Interesting thing about wood itself is that it contains a lot of oxygen in the chemical composition. So even around 40% of wood chemically is oxygen. So this is also why there can be combustion of wood even when there is not enough oxygen in the zone. Okay, so is it something new, or is it something that we've known for some time? I will give you some examples of historical statements, and you will see that the influence of air on fire was understood very early. Here we have a quote from Chief James Braidwood, who is told to be the first founder of urban professional fire brigade in Edinburgh in 1824, if I remember correctly. And he wrote a book in which he said, "The men of the fire brigade were taught to prevent, as much as possible, the access of air to the burning materials. What the open door do of the ash pits is to the furnace of a steam boiler, the open street door is to the house on fire. In both cases, the door gives vital air to the flames." So even though we understand the combustion triangle or tetrahedron correctly, we know that the tactical understanding was already present so many years ago. Then we have his successor, Chief Sir Iry Massey Shaw, years later, who also said, "I'm strongly of the opinion that many heavy losses in past times may be traced to injudicious breaking of windows," so like not justified breaking of windows, "for the purpose of entering by means of ladders, when it might have been quite possible to pass up and down the stairs, and at the same time to exclude from the room in danger all air." So we have to understand that firefighters back in the days had great, fantasy, and they preferred to enter by windows with breaking glass because it was more heroic and so on. Perhaps, I don't know, but it was his observation that it was the cause of many heavy losses. So because you can close the door once you open it, but you cannot put the window back if you break the glass. And then even years later, there was another chief, Alimer Firebrace, who said something that I will quote right now. He was British. "An American fire chief told me that he rubbed in the principle of ventilating by making his recruits extinguish a fire in a drilled building with all ventilation shut off. They had a grueling time of it. Then he gave them a similar fire with all the building vented, which means all access of air. They never forgot the lesson. Ventilating must be done at the right time. Air must not be encouraged to flow into a building until lines of hose are laid out and sufficient water is available." So these three historical examples tell us that it's not something new, and it was understood from early years of organized firefighting that air plays a vital role. But honestly, these are observations, and we are living in a world that is largely based on the scientific understanding. And in CFBTPL, we also focus to provide scientific justification for anything that we try to teach to firefighters. Of course, we don't make them read books from professors, but we are trying to translate the difficult technical language into simple concepts that are they need to be simple because they need to be applied in matters of split seconds, so they cannot be very complex. So first we explain all the background, all the justification, and once everybody understands, we agree on a simple concept. It's something that we like to call a non-negotiable, which means that it's a rule that it's not to be negotiated. Once we understand that this is how science tells us that things work, we are not negotiating with anything, we are applying this. And the phrase non-negotiable is coming from my dear friend and colleague John McDonough from Australia, one of the 4 authors of a very good book called 3D Firefighting, which in early 2000s, I may say, revolutionized the approach globally to fighting fires in structures. Okay, but if we're trying to be scientific, let's remember that it's already over 100 years ago that we have available the scientific research from a gentleman called William Thornton. And in 1917, he examined the relation of oxygen to the heat of combustion of organic compounds. We have to remember this. It was for organic compounds because he didn't have any artificial materials at that time to examine. So there were only organic things in the world. Nice times. And he scientifically proved that the amount of heat created in the process of combustion is directly proportional to the mass of air, and more specifically to the mass of oxygen delivered to the process. And it's almost not important what kind of fuel is being combusted because it's always 13.1 megajoules per kilogram of oxygen and their differences between different fuels only have like less than 5% of influence. We don't have to exactly remember that it's 13.1 or 24 or whatever other number. We have to understand that when we have a fire, it is directly the axis of oxygen that will dictate how much heat is created in the reaction of combustion. So, of course, the intensity of fire depends on other factors as well. For example, if the fuel is highly combustible, if its location, its situation, if it's situated in a way that it can easily ignite. For example, we know that fires travel upwards faster, then they travel horizontally slower, and they travel downwards even slower, and the difference can be between upwards and downwards even 30 times the difference. So that's one thing. But if we are considering a room on fire in any house, basically the configuration of combustible materials is comparable. So we have to understand that it will always be the axis of oxygen or air, to be more general, that will dictate how much the fire is burning. And it's a very important concept for the topic that I'm discussing, which is called tactical ventilation. So in the 70s, the National Institute of Science and Technology in the United States re-examined the research from William Thornton, because they already had some synthetic fuels, and surprisingly, the rule still applies, even though we know that synthetic fuels can produce twice as much heat, but only if they have the oxygen. And if we take a room and the geometry of the room is constant, and we put old furniture in it where there's no artificial material, synthetic material, the velocity of fire will be, or the intensity of fire will be different than the intensity of a fire in modern times, where majority or even all materials are almost entirely synthetic. So we have to understand that it's already been a century of knowledge of this, of scientifically proven knowledge. This is an established fact. We cannot discuss with that. We can use this fact to our advantage, and sometimes it is advisable to add air, but most of the time we have to remember that unless we take steps like Chief Shaw mentioned, unless we have another gentleman, Firebrace, mentioned, unless we have extinguishing water ready on the nozzle, we should not add air to any fire. And soon we will also find out that it's becoming even more and more of a true. So, okay, now we can say about burning regimes, which is something that needs to be understood as well. When the fire starts, it's controlled by fuel. So we are referring to these fires as fuel-controlled fires. So in the initial stage, when there is low dynamics of combustion and oxygen is sufficient, there's enough oxygen or more than enough oxygen, it will be the fuel that will dictate the intensity of the fire. But there will come a time in any fire, or most of the fires, not all the fires develop, sometimes the fire dies out because it doesn't have any fuel in the vicinity to light something up. Then any fire, the majority of fires can develop. There's larger surface being involved, it produces more gaseous fuel, and it demands more oxygen. There will become a moment when the oxygen is not sufficient, because it's coming through a window or through a door, or maybe it's just the oxygen that is present in the fire, which in the room which is closed. So there will become a stage which we call a ventilation controlled fire. It's a more important for firefighters to understand this mechanism, this threat. And even if we refer to scientific formulas, we will see that heat release rate, so the rate at which heat is produced, largely depends on the geometry of the openings. Here in this equation, which is coming from Kunio Kawagoe, the Japanese scientist working in the 1940s and so on, also responsible for creating many important formulas for scientific research of fire. We see that the geometry, which is expressed in A, W, and H letters in the equation, is responsible in large part for the amount of heat that is being created in the fire. Okay, let's not stop here. We have to also understand that back in the days, there was an idea of removing smoke, which helped in visibility, which helped in removing the heat contained in smoke, and it worked. It stopped working with the introduction of synthetic materials because we have now what we call the ventilation paradox. And it's a very nice comparison from my good colleague Chief Ed Harton from the United States, from Whidbey Island Fire and Rescue. Uh, and if you go to his blog cfbt-us.com and type in ventilation paradox, you can read the graphic carefully. I will just mention that once we introduce air, we also let the smoke out, but the air that is coming in has the ability to start producing even more smoke. So the idea was to remove smoke, but what we did at the same time is we introduced so much air that it created even more smoke. So it's not usually it's not helpful, and it's because of the introduction of synthetic materials. So, as I mentioned, the National Institute of Standards and Technology, the 70s, examined the Thornton rule, and they created the what we call fire curve. So we know that the fire develops, then it transitions through a stage which is called flashover. Flashover is a moment when by the ignition of hot gases, all the combustible surfaces also ignite and we have full room involvement. And then it reaches a stable phase and then it starts to die out. Of course, we're not accounting for any fire service intervention in that curve. Now, more recently, around 2008 and 9 and 10 and onwards, the UL, Underwriters Laboratories Firefighter Safety Research Institute, FSRI, they conducted numerous very valuable researches with great funding, with great understanding, because they've always worked with the panels from firefighters, and they've identified major changes in fire behavior. First of all, it will all be happen much faster, and there will be very characteristic points in many fires. So there will be ignition, just like in the previous case. There will be growth. It's FC, fuel controlled fire. There comes a point when it's growing so fast that it's starting to need more oxygen that is available. So it's becoming VC, ventilation controlled. Then we have the initial decay. The fire is slowing down because it doesn't have the necessary oxygen. And then we have ventilation. It can be by fire department, FD, or other for other cause, like window breaks, or somebody opens the door trying to see what's happening. And then we have, again, transition to the ventilation controlled fire with the occurrence of the phenomena called flashover. Flashover is, as I said, total room involvement. So it grows and then the fire is becoming fully developed. Now we have to understand that if we start opening up, it can create even more heat. For example, if we start to cut the roof, which is a very popular tactic, for example, in the United States, if we don't block the incoming oxygen, we will cause the masses of smoke go through an opening and the fire will accelerate even more. Okay. And then, of course, we can add suppression, hopefully not at this final stage, but in the previous stage. But let's say suppression is when we stop creating heat because we interfere with combustion process, sometimes taking away the available fuel, but most of the times taking away the heat by water. And by creating steam, we are also blocking the oxygen. So then we are starting to decrease the involvement of fuel, which changes the fire dynamics, and at some point it's again becoming fuel controlled fire and is going to decay, and hopefully we will be able to extinguish it. We have a saying that have you seen a fire that is still burning? No, because every fire goes out, but we should rather aim at our activities, putting out the fire, not the time or running out of fuel. So then we will see a video here, and I'll read to you first the comments under the video. All activity altering the ventilation profile, and the ventilation profile is the geometry of windows basically and doors, will may lead to dynamic changes of fire behavior. And James Braidwood wrote in his book many years ago, "He who controls the air controls the fire." So let's play the video. Okay, it's slightly accelerated. If you look to the window next to the vehicle, you will see that there is a fire over there. You see the window curtains are beginning to fall down. They are synthetic, they melted. But we don't see the flame, yes, because the fire is suffocated. It doesn't have air, so it consumed the air that was present in the room and cannot develop anymore. Now we have a neighbor. Let's call the person a neighbor. He's a nice neighbor trying to help, but he doesn't understand the dynamics of fire, and well, it's not his job. When he opens the door, we immediately see that the flame appears. We are going towards the flashover. Now we also see that the window breaks because windows are not flexible materials. They get tension from heating on one side, cooling on the other. They break, and once they break, they also let out some smoke and introduce some air. When the smoke is going out, it's also creating more space for air. So it's a process. It's like complex, not so complex, but it's more than a simple process. Now we see there's basically a flashover. Everything is burning. So that's it. It's one example of how changing of the ventilation profile, which is again the geometry of openings and windows and doors and other openings that are able to let the smoke out and let the air in. When we change the ventilation profile, the fire dynamics have to change because we're talking about laws of nature. There's no will, there's no want, there's no desire here, it's pure science. There will be spread of fire. Okay, so there was a research that I mentioned to you that compared a fire in a single room, and the one fire was made with natural materials and another was made with synthetic materials. So basically we can understand that we no longer have natural materials in our interiors, or there's very little of them. Its vast majority or nearly all materials are synthetic because we are not using wooden chairs or wooden tables anymore. It's a chipboard. So there's wood, but there's plenty of glue. It has the veneer on it, the coating. There's foams, there's artificial materials that resemble leather or other things. We saw that the window curtain is not burning, it's melting. So it's basically, as firefighters in English-speaking countries say, it's solidified benzene or solidified diesel, because it's coming um, from basically oil, and it's a hydrocarbon. But I will go back to one example that I used, the example of water. Water as a natural substance is very stable, has a very strong bonds between the particles. Now, whatever is synthetic made by humans, it's engineered to be quick, cheap, light, and so on, but it's not very stable. So when we add some energy to it, like heat, it easily decomposes. So we see that in comparison of two fires, the synthetic materials, they gave up faster. The very severe conditions were created a lot earlier, in an earlier stage of the development, and also they reached higher temperature, which is not maybe so important because there's a certain temperature that victims and firefighters can withstand. But basically the dynamics of the fire is surprisingly, not surprisingly, it's not surprising, it's also almost scary. uh, for sure we have to respect the fires that are in modern environments. So this complicated graphic shows multiple possible scenarios. The blue line is showing that the fire did not develop, there was no fuel, the conditions were not right. Like you put something like a cigarette in a trash can. Oh, it starts to burn a little bit, but there's not a lot of fuel. There's something wet, and the fire dies out. Okay, no problem. Now we have the red line. The fire was developing, but it reached the FCVC point, which is the point of transition between fuel-controlled fire and ventilation-controlled fire. But it didn't have additional air. Somebody went out of the house, so one room burned, it was closed, and nothing else burned. No problem also. I mean, there's a problem, of course, but the fire didn't spread. And there's a black line, which represents the traditional development of fire with a presence of air. So it's going through the phenomena of oxygen and, the phenomena of flashover, and fuel burns out eventually and fire goes out. But we can also have very violent or dynamic, perhaps it's a better word, dynamic phenomena. Like under number 4, we have something that is called backdraft. It's like it's almost like an explosion. It's throwing out of a fireball through the door, because there's a lot of heat, a lot of smoke. Somebody opens the door, the air goes in and mixes with the fuel, and it ignites. When it ignites, it creates heat. When it creates heat, it raises temperature. And as I mentioned to you before, when it raises temperature, both pressure and volume also increase. So we have this understanding that it's accelerating, the flame is accelerating towards the opening, the door, for example. So in effect, we see a ball of fire being thrown out of the door. If it's not this case, then in some other similar case, there can be a fire gas ignition, and the fire gas ignition, it can be more dynamic, less dynamic. It's basically some kind of combustion of fire gases that are either mixed with air or are mixing with air in the process. If they are mixing with air, the burning is slower. If they are already mixed and they have a spark, an ignition source, or burning embers, or flame traveling, then the reaction is a lot more dynamic. So it creates more pressure buildup. So it can be more devastating for buildings, but also very harmful for people, because people don't take pressure waves very very well. Like if the wave hits the chest, it can create major injuries. Also the ears, of course, but the chest, ears can have a problem. Then we can have a problem with hearing. But if it hits the chest, it basically it acts like a mechanical force. Okay, so if we again compare the old fire to a new fire, we see that one thing didn't change. First, we have green line and, let's say, violet line. The green line is representing oxygen concentration, and the other line, the violet line, represents ceiling temperature. We can see that they are almost mirror images. So when the oxygen is decreasing, which means it's burning, the temperature is increasing. But it's not different to old fires. Okay, we have some specific points on this graph, but in old cases it was slower, but still the relation was the same or almost identical. They are also almost mirror images, which is a proof that air controls the fire. So as Chief Braidwood said, he who controls the air controls the fire. Okay, so when we understand this, it's now time to move to how firefighters can control air to their benefit, which is called tactical ventilation. So after this introduction, we're getting to the point. So I'd like to mention that all my knowledge is coming from my mentors. I know I don't look like I'm looking on the picture right now, but it's been a couple of years. This is a great mentor of mine, and I have the privilege of calling him my colleague, and he did a lot of help for me. So I'd like to give credit to Paul Grimwood, whom I respect greatly. And large portion of my knowledge is coming from his books, his articles, which he's written literally hundreds, and also through direct conversations, which are always very valuable. So Paul Grimwood first published the concept of tactical ventilation because it's exactly his term in the late 80s of the last century, and the concept is thoroughly explained in his book called Fog Attack. So what is tactical ventilation? He refers to it as venting actions, so actions that refer to ventilation that are being done by unseen firefighters used to gain control of a fire building's internal environment to the advantage of firefighting and rescue teams working within. So these actions, again, are used to gain control, which means tactical advantage. So that's why it's called tactical ventilation. It's as simple as that, but it's not easy to do. So as time passes and technology advances, we have more and more means of doing that, but we also have to remember that we are dealing with fires that have changed over the last 30, 40, or 50 years, depending on which place on earth you are living in, because more advanced, technologically advanced countries introduced synthetics to their interiors a lot earlier than some other countries, perhaps. But certainly, whoever is in service today most likely saw usually the nature of synthetic fuels. It's not common to meet someone who who is still active in duty. There was firefighting prior to, let's say, 1980s, and remembers maybe some cases of fires which did not involve synthetic materials. So what are some exemplary actions within tactical ventilation? We can attempt to release smoke or direct smoke somewhere by either natural ways or forced ways, via horizontal or vertical openings, which are either made by us or are existing in the building. But we also can think of closing down of the structure, which is called anti-ventilation. But what is essential for firefighters to understand that most dangerous opening that can be created in any building, in any structure, is the door that they are using to enter. Because firefighters may have the impression that they are controlling the situation, but they have to remember that once they open the door, they have started to add oxygen to the fire. So it's like a time bomb that started ticking. So to explain the concept, I will make a short, not a summary, but like an overview. Basically, this slide should be called overview. We are talking either about ventilation, which means gas exchange meaning smoke goes out, air goes in, or anti-ventilation, which means stopping gas exchange, isolation. So by principle, we can either make it by some means, which is forced ventilation, or we can just create conditions, which is gravitational or natural ventilation. If we are forcing ventilation, we can use overpressure or underpressure by either a fan, a ventilator, or hydraulically by a nozzle that applies water. But if we are talking about natural ventilation, we can either use vertical or horizontal openings. And to talk about isolation, we can isolate the fire fully or just partially. We can do this by either existing means. For example, we can close the door, or we can do this by the means that we bring to the fire scene, like the smoke curtain, which I will cover later in the lecture. Here, technique is door control or smoke curtain. But we also have to remember there is a very strong factor that can influence everything, and it is the wind. We have to remember that wind is part of tactical ventilation, and I'm sometimes very worried that many firefighters do not remember to include wind conditions in their size up, in the reconnaissance of fire. At the very beginning, when we are coming to any fire, we have to make a quick check in our mind. Is there wind, and can it influence my fire, my outcome of my firefighting actions? Okay. So in order to understand reconnaissance or size up, as we call it, we have to also remember that there is we can examine flows. So here's a simple example of the building, and we see that in the window, which we can see from the street, we have what we call bi-directional flow. So in one opening, we have two flows that are going against each other. One is the outflow of smoke, and the second is inflow of air. So it is very likely, very probable that it is the only opening to that volume, to that area, because we don't see full smoke or full air being sucked in, being pulled in with under pressure. So bidirectional flows are telling us something. Then we can have unidirectional flow. When we go from the street, we see that the window is full of smoke. So definitely there has to be another opening made to that volume, to that compartment, or to this apartment or whatever. So it tells us already from the street, before we even enter the building, that this fire may develop as we prepare to enter. So we must not lose time. Perhaps it's advisable, it's smart to send out some people quickly and try to maybe isolate the fire before we are ready with water. Because if the intervention is fast and we are coming at early stages of development, we can significantly influence the situation and stop the fire when we isolate. In isolation, because of the synthetic materials, because of their tendency to have such great velocity of spread, this isolation technique is becoming more and more advised and smart and useful. We also see that there's, in this case, from tactical point of view, if there's an opening at the staircase, it's rather likely that the staircase will also get smoked. So we have to remember that one of the most important things to secure is escape routes for other residents of that building. And we can have forced flow with wind impact. It is still what we call natural ventilation, because we didn't do anything to make it so, but we're seeing that wind is entering the window, it's very strong, and if it's not flowing out at the same time through the same window, it means there is an opening and it's going to another side, and most likely causing a lot of problems. Because when we look at the picture, every firefighter will immediately understand that it's a very bad situation that we have to quickly control and reverse, because now we have occupants trapped in upper parts. And of course, in majority of cases, it is so that the buildings have to defend themselves, protect themselves. But we have some cases, and recent cases like Grenfell fire, when we saw that combustible materials used to finish the outer part of the structure were very much responsible for the tragic effect of this fire. Okay, if we want to understand how we want to release smoke, we have to understand that it's dependent of two things. One, the ventilation will be faster. So here we have efficiency of this process. The ventilation will be faster if the smoke is hotter, but also it will be faster if the inlet is bigger than the outlet. We see that the inlet to outlet ratio should be preferably 2 or more. So if we look down at the graph, at the horizontal line, we see 2 is more or less in the middle. We go up and see that it's a high effectiveness of that process. If we only have 1 on the lower axis, on the horizontal axis, we see that it's already significantly smaller for 500 degrees. And we have half, which means that inlet to outlet, that the outlet is twice as big as the inlet. We have more windows than we have doors on the bottom. Then the efficiency of smoke removal is not great. But it's not, this is just to understand the principle that inlets should be bigger if you want to let out smoke. And of course, it's more advisable that we let out smoke when the fire is already extinguished, because if we want to make inlets big and the fire is not extinguished, it's maybe not such a good idea, because then we are creating more heat than that we are able to extract by the openings. Okay, just for the principle. Now we see a video of wind impacted fire. Let's play the video. On the left, we see it's an experiment from NIST. On the left, we see a window that will soon fail. Please see on the right. This is the approach. It's the entry to that room. upper part is smoke, lower part is air. Firefighters can crawl in and start to extinguish. But when the window breaks, there's a terribly bad change of situation. Suddenly, everything is an outlet. So we have fire from up to down in the entrance to the room, and it's only because the window failed. And it's a situation where firefighters die. So we cannot overemphasize the importance of reconnaissance of wind. We have to understand that wind can kill firefighters. It's absolutely of greatest importance. Okay, let's go on. Let's try to change the slide here. Now let's take 4 examples of the same fire, and we will just play with the direction of wind. In first case, we see that there's some openings in the structure. So okay, no problem. The wind is at the entrance. It will go out on the upper part, and it will go out on the part of the fire room, and it's helping us. So no problem. Another case is such. In case 2, okay, we have some wind towards us. Maybe it will take some smoke towards us as well, but it will still help us and remove smoke through the windows, which are either opened or they broke. Now situation 3 is quite catastrophic because we are working against the wind. So wind will push out hot smoke with air through one of the available windows, but it will also push the fire on the approaching fire team. So it's a very bad situation. So in this case, we should not attack the fire if we are working against the wind. We should rather look for other ways to attack the fire. And in fourth case, and we know that we don't have 4 cases. We have as many cases as there are angles in a circle, yeah. But let's say 4 sides of the building, so 4 cases of wind impact. Still, in that fourth case, we are also working in a very disadvantageous position because we will also have smoke going on our firefighters. Now, this is a real case from a fire near me, and some of my colleagues were in that fire. It's a chicken house on the open field, and we have to understand that even if we are saying that for high buildings the wind is the problem, but also we have to understand that for low buildings in an open, wind is still a problem. When we want to make reconnaissance, we see that the smoke is showing us that there's wind impacting the fire. You have to understand that in this moment we have 3 firefighters inside. Okay, it's a short video, but you can first of all hear the wind. It's very strong. It was 20 to 40 kilometers per hour because we checked that. We then have to make analysis from that fire because 5 firefighters were injured, 3 were sustained burns that were inside, and 2 outside, they sustained smoke inhalation. The problem was that the fire was developing in a chicken house. Everything was wet. There were no animals inside, but the building was prepared to have animals inside. And there was some light colored smoke. So firefighters interpreted it's from hay, from dry grass that is used for, accommodating the chickens, the birds. But because of the heat that was gathered, and it was not easily noticed because the building is tall, so the heat, of course, accumulated in the upper parts. There was a process of melting of plastic windows. So there became a point when this happened as a domino effect. 1 window failing, 3 windows failing, 7 windows failing, and all of a sudden we have an inrush of strong wind to this structure. And you have to also understand that the structure is not like an open field for playing football. It's full of cages and wires and so on. So it was a very problematic situation. It resulted, everything is fine, nobody got killed, nobody got seriously injured, but it was a case that made also firefighters understand that wind is a very powerful factor that can change everything in a response. Okay, let's move on. So we can also study, so I recommend that you also study, try to see the effects of built up areas on wind, the microclimate of cities, and I assume that just like in Polish case, it's not entirely new, because we found some articles from 1940s by some engineers examining the impact of wind on fires. So like in every fire service, we discover the wheel every couple of years, and then we're happy with the new discovery that was already an old discovery. But you have to understand that depending on the geometry, there will be different effects. So there will be also a lot of turbulences, like you see on those illustrations here. Okay, what is very useful is the Beaufort scale to examine the impact of wind. If you see the Beaufort scale, you can address some visible factors like movement of smoke. Okay, if it rises vertically, no problem. If for example, you feel the wind on the face, still not such a big problem, but there's a moment in which you start to see that the wind is impacting the fire, and it's more or less 14 kilometers per hour, 15, 13. Well, it's not a sharp, it's not a one spot, but it's more or less this order of magnitude. When if you see leaves and small branches, small twigs in constant motions on trees, if you have a flag and it's extended, it's not going directly downwards. If things are flying on the street like papers or small garbage or leaves, you have to take into consideration that whatever you do with the fire will also be impacted by wind. So here's one of the good practical ways of recognizing that. We also have cases from NIST, the National Institute of Standards and Technology. There was a case, there was a fire where also firefighters died in the fire. We see on the upper part where it says 4.9 meters span of windows, there was a space separated from the outside by only windows, large glass wall, and firefighters went in from bottom of the picture, open front door, trying to find the fire. And when the windows broke, the fire filled in an entire structure. So they were working against the wind, and it was the cause of their death, that wind destroyed the windows, because it also extends some physical force on a large surface, and then it started blowing air to the fire and moving hot gases with great velocity towards the firefighters, who eventually lost their lives in this fire. Okay, and another factor for reconnaissance is you can look for some unexpected or surprising behavior. Like here you see with the yellow-red arrow that the smoke, that from the color of the smoke, we see that it should be very hot, which means it should be very buoyant. It should have great tendency to rise upwards, and it's being pushed downwards. It's exactly by the turbulence caused by wind. So if you see cases like that, which we call smoke reading, is something that has to alert you. Okay, so then we have how we can counteract is, for example, by isolation and by use of forced ventilation. In case A, on the upper part, we see the wind problem of fire. So black arrows is the smoke, and blue arrows is the air. So we can attempt to either close the door or use the smoke curtain, which I will soon also describe, and also positive pressure ventilation in order to reverse the effect and clear out the smoked area for evacuation, for example, and then focus on the fire. There's also in fires a special case described by one Polish professor, Professor Jerzy Wolanin, which he called aerodynamic impact. It's sort of a special case, and it refers to something that I've mentioned to you when I was talking about stack effect, chimney effect, like a syringe, like a piston, when there's a lot of hot smoke and there's sudden opening of an outlet or creation of outlet, like in this case there's a skylight that broke. The air is starting to move upwards and it creates an under pressure area low, which is causing for the air to be pulled in by the under pressure. So it looks like an impact of air. It's not wind. It's like it's sort of wind, but not from over pressure. It's not gusts of wind coming from outside, but it's a pulling in of oxygen. And of course, the effect on the combustion is the same. The combustion gets more dynamic. So ULFSRI, the institute, made a number of experiments when they tried to understand how we can combat or counteract the effect of air. So one case is we can try to isolate the fire. There's a technique called door control, when we have first of all, we see that if the fire on this graphic, we see if the air is consumed, there will be drop of intensity of fire, and when we open the door, like on this graphic here by 2 arrows, there will be again increase of the fire. It's a single-story family house and double-story family house. But when then they moved to trying to counteract, we see that the door open was the cause for the fire to accelerate, and it's marked by red line, but the orange line shows that the firefighters went inside and another firefighter was at the door and kept the door as much closed as possible, only allowing the hose line with water to be pulled in, and he was also assisting in pulling in that line. And you see that for a number of minutes the fire did not increase. So it's one way of counteracting the effects of oxygen on fire. And it's exactly the definition of tactical ventilation, because we are using the ventilation profile or gas exchange conditions for the tactical benefit of firefighting. So there cannot be more perfect, by definition, more perfect action of tactical ventilation than this. And okay. Fire isolation, let's see. Yeah, okay. We have a fire. It's a small scale model that I'm showing to firefighters. And if you want to put out the fire, you block the oxygen, just look a couple seconds and there's no flame anymore over here. So we don't have the flame. Of course, now is the time for cooling. If we don't cool it, the fire can go back. But by definition, if you block the air, you can put out the fire in such a way. Okay, so let's now talk about some form of ventilation. So we will start by something that is probably one of the oldest kinds of knowledge, which is hydraulic ventilation. So there's a great deal of information on that in the book of my dear colleague Stefan Sartqvist from Sweden. And I have to tell you that if you take this title of the book and you put it in Google, you will get a free copyright book in PDF. So I greatly recommend this book. It contains great deal of knowledge on water and other extinguishing agents. And one of the aspects that Dr. Stefan Sartqvist is focusing on is the fact that spray patterns move air. Now, it's not my point to exactly kill you with all these equations and all that kind of counting and calculating, but you have to understand if you set the nozzle to an example of 270 liters per minute and you will make the geometry 1 meter of diameter, you will pull inside the water spray and push along with it almost 20,000 cubic meters of air per hour. So you have to understand that this is equivalent to a small positive pressure ventilation fan. So it can either be good or bad, depending if we want this result or not. So pushing gases with hydraulic ventilation is something that we've been looking at for many years now, and it can be advantages, but it can also be disadvantages. We have to understand there's a certain disadvantageous situation if we have a victim between fire and exit of smoke. Whatever we push to the victim. So we have to make good reconnaissance before we move on to that. Okay, here's another video. There is a very simple demonstration how changing of patterns is changing the aerodynamics. The video is slightly faulty, so there will be a small hiccup here. It's like repeating and repeating. You can see that I'm making the stream more wide, and as I do that, I push out air so the door opens. Yes? Okay, so the door opens because I'm moving a lot of air, so there's demand, there's under pressure that I'm creating. So at the same principle, I can push out smoke. And when I go back to straight stream, the door will close. It's slightly, there's a slight angle on this. Okay, we move on. But there are also devices that can have this similar effect. One device that was shown to us by a firefighter from Chicago is called Hydrovent. You can see that this artificial smoke is being pulled out by a device that is not doesn't have to be controlled by a human. You just put it in place and it extracts smoke itself. It's called Hydrovent, and what it can also do, okay, let's show it in another video with real fire. Now you see there's a gentleman on the right. It's Kevin O'Donnell, our dear friend who visited us. He's a firefighter who invented this, working just on outside of Chicago Fire Department. And on the left side, you see the thermal camera image. So let's play the video. And over here, also you have to know that he has this nozzle also has an opening on the inside, so it puts water inside and also pulls the smoke outside. So we will see, you can count seconds, we will see that it's very fast. See the thermal image now. As the fire is dying out, there's less and less yellow color because water is flowing inside and hot gas is moving outside. Also, you can see that on the entrance on the door, it's creating very good conditions for firefighters to enter. So if you put this and then you move to the door, it's not, you don't need to operate this device, it's simply allowing you to enter. But the main key point behind this is that hydraulic ventilation is a very powerful tool that firefighters have. Okay. So yeah, that's the end of part one. Thank you for your attention. If you have any questions, the organizers have envisaged the way of asking them, but you can also contact me under this email and tell me your questions.
Wow, very interesting. Very interesting also from that point of view that tactical ventilation is not only the thing that increases the efficiency in fire extinguishing, it also gives this solidarity and, in the team, and basically the safety itself for firefighter. So, lives of firefighters are priceless. So, Simonas, how did you like the presentation?
Oh, very much. It's very interesting to look at that. We don't have so much like examples in Lithuania, so interesting very much.
Yeah,
I liked it very much.
I do understand that on a training ground in Valčiūnai, we theoretically, at least, we could try to do this kind of tests or training program. How do you think?
Yeah, it's absolutely there is possibility. We have like training or drilling building. It's like imitation of urban territory.
Okay.
So yeah, there's like we have how to say methodics of starting the fire, real fire in that building, and for learning, for teaching young firefighters. So I think there is all possibilities.
So I do understand that in Lithuania and probably in all other Baltic states, sometimes we do have already existing training drill grounds, but we do not fully use all those possibilities that we could. That's why I think such persons like Szymon Kokot-Gura is very valuable actually for everybody of us to hear from them, and afterwards to try and to test this kind of thing. It's I don't know if it's safe. Can you tell me?
I know. I've thinking about Szymon Kokot-Gura. It's like I think we have to take him, place him in Lithuania for maybe 1 month, and everybody must come to see and talk with him and learn from him.
Yeah, he's really a firefighting guru. So Szymon, be prepared. We're waiting for you for 1 month at least. So
at least.
Yeah. So Szymon, the stage is yours. The second part of tactical ventilation, very interesting topic, and just please be there. Please watch it and hear it. Szymon, the stage is yours. Thank you.
Hello everyone, welcome again to the second part of the presentation on tactical ventilation that I'm delivering specifically for members and participants of the Baltic Fire Forum. So you've seen the first part. Please, maybe small quiz to move you up a little bit, to warm you up. I changed one detail in the room. I will tell you if I don't forget. I will tell you in the end of the presentation. Okay, so we've covered basic fire phenomena. We've covered some aspects of modern fires, fire isolation, and also hydraulic ventilation, which is a very powerful tool which can be used with forced ventilation. And now we'll move to forced ventilation. It's a very broad topic. We can speak about it for a week even, but I will try to give you the summary of the most important fundamental facts about and principles about positive pressure ventilation that we've learned from our colleagues around the world, from scientific research, and from our own tests so far. Okay, forced ventilation. We will move from under pressure to overpressure. Just like with the hydraulic ventilation, you saw we can push air with water through the structure, which we don't do a lot. It's rather a result, an accompanying result of our applying water. But if you want to pull out, then we are talking about negative pressure. So yesterday you saw that there was standing a firefighter was standing next to the window, and he was applying. That firefighter was me, by the way. So I was applying the spray to the window, and I was causing the door to open, which means that I was creating under pressure inside the structure. So I was pulling out smoke. The same door, if I stood in front of them and if I would apply water in that door, that would be pushing inside the structure, because our point of reference is the structure itself, because it contains the fire and it contains the smoke. Okay, let's see smoke extraction. Here's a video of a concept. We have a structure. Put down some volume. Okay, we have a structure. It's a basement which is full of smoke after extinguishing, and we want to remove it. So we have a small inlet. You remember that the inlet should be bigger. We're trying to also measure the velocity, 3.6, 5.1, yeah, 3.0, okay, 3.2 meters per second. So it's very decent. It's not bad. There's some noticeable velocity, and the fan is extracting smoke from basement. It's what we call an acquired structure burn. Acquired structure, which means we have acquired this structure. It's purposed for demolition, and we're making exercise. Over here you see a fan that has a special mounting device, and it's an electrical fan, and therefore it can work in smoke atmosphere. It doesn't have a combustion engine, so there's no problem for it, and it will not die because of lack of oxygen. So we mount it towards the ceiling because it is where hot gases are gathered. Okay, this is the voluntary fire brigade that helped us, so I'm sending them greetings. And we were creating some teaching materials, so there it is. And this is the inlet which you just saw. Okay, the inlet is small, so the velocity of the gas was significant. So it's one of the ways of extracting. Now we have reversed the situation, and we are putting the fan next to this window, so we can do either extraction by door, extraction by window, either way. Well, I have to again emphasize, you cannot do this with just any fan, any ventilator. First, it has to be a fan that can work with smoke, so no petrol fan, no petrol engine. And secondly, also make sure that this is a fan designed to remove smoke through it. It will, of course, make the fan very dirty because the smoke is dirty, so it's not always the correct thing. But sometimes you just have no other way. Okay, I would like to share with you more on positive pressure ventilation, because as I understand, all the participants that are listening to me most likely are familiar with more positive pressure ventilation than negative pressure ventilation that I just presented to you. We have here a summary of photos from what we call backyard tests with cold flows that we did in my fire brigade with the, if I remember, let's count, 1, 2, 3, 4, 5, 6, 7 different models of fans from different manufacturers. We call them backyard tests because we take some measurements and we do some testing, but it's not exactly scientific. I mean, there are some measurements, but we were not controlling all aspects of the tests for scientific purposes, but rather we wanted to see some principles in practice. So we used smoke machines to put the artificial smoke, which was not harmful for the fan, through the fan to make the stream of the fan, the air stream of the fan, visible. We use some small pieces of plastic bags that we put inside the door. If we make a zoom to this slide again, then you will see that picture on the up. It's third picture from the right. It contains some images of small plastic pieces of small plastic bags that we put inside the door, and we wanted to see if they are moving in one direction or another. I highly recommend to you such very simple methods of examining your fans, and I will tell you right now what we did, and you can try to also replicate that. We also measured concentration of carbon dioxide, CO2, because we at that time in 2014 used petrol driven fans, so we have some also understanding of what the fans create, because we have to always be aware that whatever petrol driven equipment we are using, it can be pumps, it can be power generators, electricity generators, it can be positive pressure fans, we can create an unhealthy or even dangerous atmosphere by the presence of exhaust fumes. We also look at the attachments to apply water mist from the fan, and here you have some fans on the bottom part and our participants. So okay, let's see what was done. So we understand this will also be explained a little bit further in the presentation. So we made some measurements for geometry of openings, because we understand that the geometry is important. In the first part, we spoke about natural ventilation and that the inlet, the surface of the inlet opening should be bigger, preferably from the surface or total surface of the outlet. But in case of positive pressure ventilation, it's exactly the other way around. The outlet should be bigger than inlet. I will go back to this in greater detail a little bit later on. Okay, so here we have make and model. So you see, and then we have placed the fan in different distances from the inlet. So at the inlet, which is the first column, 0 meters, and then every half a meter up to 5 meters away. Then in the part in the column when it says velocity of air at optimal distance with smoke stopper, I will comment on that. And then you have CO, pardon me, I now understand that I said carbon dioxide. Of course, I meant carbon monoxide. So CO, not CO2, because it's the CO that is a harmful substance, because it has the tendency to connect with hemoglobin, and at the same time it blocks oxygen from connecting with hemoglobin. So by nature it's a suffocating agent. We say it's toxic or harmful, but it's a generic term. It's exactly the mechanism is suffocating. Okay, so what are we seeing here in this slide? We are seeing one important thing that I wanted to highlight in green, that depending on the model of the fan, there was a different optimal distance. Now, why is that? We have to say that we looked at the engines. Engines were mostly the same or very similar, with very comparable horsepower. The diameters of the rotating parts were slightly different. So we had smaller fans, bigger fans, but we see that for different, and there are some very poor performance we see here, not so good fans that were not able to move the air significantly. But we also see that the first row is half a meter away was the best performance, and in the 1, 2, 3, fourth row, the leader was at 4.5 meter distance, was the best performance. The performance was measured by velocity of air in the outlet, because in practical terms, you want to understand how much your efficiency, your effectiveness is determined by the fact of how much you are exactly ejecting from your structure. This is your measure of your success. The amount of smoke that you are removing from your structure. So the easy measurement is velocity of air in the outlet. Then you can multiply it by the surface of the window, and then you exactly have your cubic meters per second. Okay. There's also another column which says velocity of air in the outlet, and in each case, when we use the smoke stopper, to which again I will return in a couple slides, it always increased the efficiency. So you have to remember that if you're using positive pressure ventilation, your effectiveness will be increased if you use this tool. Okay. So why the differences? Why such great differences? We have to understand that there's a different construction of fans. Fans were first created in the 90s, maybe not first created. The first use of fans for firefighting was in the 90s. There was a company called Tempest who made fans for preparing hot air balloons for traveling, because there were many fires. There was not a good way to prepare the hot air balloon to be filled with the hot air, which was coming directly from the flames. So there was a lot of fires, and then, misfortunes and mishappenings. So there was a gentleman who created a fan in order to initially fill the balloon with cold air, so it creates a shape, and then start heating it, then it creates buoyancy and it rises, and so on. So this was witnessed by a firefighter who had an idea that it would be nice to have such a fan to remove smoke more quickly from a structure. So and these early fans, we will refer to them as conventional fans, because their construction was like we have here on the first drawing, which says traditional design with a propeller. There's only one brand that I know that uses another technology, which is called an impeller. You can look up the differences between the propeller and the impeller. Well, basically, propeller is like in a boat and a motorboat, and the impeller is like in an airplane. So on the bottom picture, the first from the right is the impeller fan, which is standing on those three crooked legs. Well, the difference is such that the propeller is mostly sucking in liquid or air, and the effect of this is pushing air, so it has to be surrounded by full ring outside the fan. But when you look at the impeller fan, you will see a cage, because it mostly pushes air, and in order to be able to do that, it has to pull air from all sides. So this is how planes work, in difference to how boats work. Well, long story short, the propeller and impeller fans both can be very effective. The difference is that the impeller fan should not be close to the ground, because it will pick up dirt, sticks, stones, and throw at whoever is crossing the path. So that's why the fan is on extended legs. But interestingly, this design is very useful because basically you can stabilize and balance the fan on any kind of surface. We've made some crazy ideas that each leg is standing on a different level, on a small wall, on one step, and on the ground. And we could balance the fan perfectly, tilt the fan, make the angle of attack different, and so on. So it's very useful, but it's a rare feature. It's rather that the mechanism that this entire body of the fan inside the frame is able to be tilted. Okay, so here are the constructional differences. And sorry, I didn't cover the middle one. The middle one is a turbo type fan. We say turbofan. The difference is here marked with some small lines on the propeller, which indicate that in this fan there's an engineered solution to focus the stream. So the stream is not becoming wide as it travels some distance from the fan, but it's rather focused. We don't say it's focused throughout entire distance that it can travel, but more focused than the previous fan. The effect of that is that there's greater velocity of the airstream, but we also see there's different geometrical shape of that fan, of that airstream. I will go back also one slide and let me show you one thing. In the first case, when the green area is on 0.5, or in the Cobra H34 case, when the green is on 1.3, and even in the second case with the Ventry and Tempest, you see that the distance is approximately 2 meters. These are all conventional or traditional construction fans. Leader is a turbo fan in this group of fans, and basically this is the only turbo fan, and we see there is a great difference in the distance for optimal performance. Now let's try to understand what is the reason for this kind of differences. Back in the days before there was enough scientific proof, scientific knowledge on how the fans work, the idea, the common sense approach was that since the fan is creating something that has the shape of a cone, which means it's round, but it's becoming wider as it goes away from the fan. The idea was that if you create what was called a seal around the entrance, you will not have back movement of smoke, back layering of smoke. And it's here shown on the left side of the slide when it says conventional construction. Okay, as time passed and there was more and more research, we understood certain things. If a manufacturer gives you a fan and it gives you some performance data, you understand that this fan is producing, for example, 20,000 cubic meters of air per hour, or larger units 30,000 or 36 or 40,000, or even very big units which are already heavy and come on trailers, come on vehicles, 60,000, 70,000, 80, 90, and 100, and even more. But let's say that when we are focusing on what we can have in a fire truck and can be picked up by a firefighter and brought to the door, we're rather around 20, 30,000 cubic meters of air per hour. Now, if we see the red area on the on the drawing, this is the seal. We have to understand that if we make a seal, also large portion of the air is not going inside the structure. So it's not making any effect on the fire. It's staying on the outside. So this is the first thing that influences the lower performance. Now, if we move the fan closer, this is why in the table you saw the performance was rather on close distances. If we move the fan closer, we are able to put the entire stream inside the door. Now the stream has a round shape and the door is a rectangle. You cannot have an ideal positioning unless you make the rectangle into a square. Then you can fill more of the air inside that shape, and then there's a better match. This is when we will speak about the smoke curtain later. It's how we make the rectangle into a square. But basically, if you bring the fan closer, you not only fit in the entire stream of air to the inside, so you are not losing any air, but also there's a principle of entrainment. It's called Venturi effect. Many engineers or technicians of fire safety understand the Venturi effect. When there's a flow and it's passing near a substance that is a liquid, so gas or fluid, it has the ability to create under pressure and take this fluid or liquid along. So in the same manner, we are doing what is called entraining air. If we bring the fan closer, we are not only pushing whatever the fan is producing, but also we're taking some air from the outside. So we can even double the air that we are pushing inside. That's why the conventional fans, which can be identified by conical shape of the stream, work better if they are closer. So if you have a fan and you want to identify which kind of a fan is it, take your smoke machine, artificial smoke, run the fan, put some smoke through it, and you will see if it's starting to get wide, then you have a conventional fan. Now with time, the technology was improved, and we now have turbo fans. Different manufacturers have different names. Over here we see one example is called Power Stream. Another manufacturer calls it LAF, laminar airflow. Another manufacturer calls it EPT, easy power technology, and so on and so on. It's not that important. Whatever it is called, the principle is one. There are additional elements of the fan that steer the air. It's like in a turbo engine for jet planes. You get greater velocity of air by the same horsepower only by engineering and designing the aerodynamic part of the fan. And as I mentioned to you before, we understood that we are using fans who have similar petrol engines with similar horsepower, and their performance, as you saw on the table, is such different. So as my colleague commented, what is best to buy? Keep your fan and invest in your training. This is your best purchase you can have. Invest in your training, understand your tool. Basically, this is the best that you can do for your firefighters, because obviously the fans will change, the equipment will improve, but once we understand the principles of operation, we will do great things with limited resources. Hey, like we always do as firefighters, yes? I'm sure everybody can relate to that as you listen to my presentation. Okay, but turbofans, in order to be able to take larger amounts of air and then train them, suck them in, pull them in, they need greater distance. So by placing them in a greater distance from the entrance, as we see on the right side of the screen, we can cause more performance. We can cause more performance. And okay, there was a let's say concern about, okay, if we create the fan that is more cylindrical and not conical, then we will have outflow of smoke in the upper part, and it's bad. At least everybody thought so. No, it's not bad at all. I mean, recent research in UL Firefighter Safety Research Institute proved with scientific methods that there will always be smoke backlayering. In fire protection, we have a concept which is called critical velocity. When we are in a garage or we are in the tunnel, we understand that there may be a fire inside, and we can understand the intensity of that fire by design. We can put so many cars inside, there's so much air that can enter. So by design, by scientific method, we can understand, okay, this will be the intensity of the fire, this will be the temperature, this will be the pressure created by this fire, and we understand what velocity we must achieve with our fan to be in order to be able to counteract the unwanted phenomena of smoke back layering. And this is a fixed engineered solution, and over here the principle is the same, although the conditions are different, because we are always at a different fire, and the fan that we have is the fan that we have. It was not designed for any particular fire. It's just a fan that on average should work on many fires. We have to also understand that the smaller fan will not work on a big fire as well as the bigger fan, and so on. But it's not based on any numbers, it's based on experience. You have to understand how it works, first of all. And secondly, okay, we are now entering a concept of tactics that is called positive pressure attack, to which I will refer soon as well. A colleague of mine, Chris Garcia, who is an author of this book, refers to that upper part of the inlet opening as the barometer. It's like the device to measure weather. Barometer, it gives you the current state, and the tendency. So if you have this upper portion of the door free from the airstream, you see some smoke movement in it. If it's very intensive, that is telling you something about your ventilation, because you don't have Superman powers to see through the window, through the walls, but by observing this barometer, you can understand if your positive pressure ventilation is acting correctly or not. If it's not acting correctly, you will have great outflow of smoke through the same door. So either fix it quickly or stop it, because you will not improve, you will rather deteriorate the situation. Okay, the reasons for that can be the doors closed inside, or there's not enough outlet area. This is the second is coming from scientific research from the same institute that I'm mentioning all the time. But the first part about closing the doors and closing windows is something that needs to be addressed with very practical measures. And the measures are simple. One of the simplest machines that humankind has invented, and it's the wedge. You have to wedge the door, wedge the windows in your desired position, because otherwise the moving stream will definitely be able to either close them or open them, rather close them. Well, for the inlet door, it's sometimes important. If the door open to the outside, then okay, wedge the door or block the door so the stream will not close them, because if you leave them like that, most likely sooner than later they will get closed, and then you're not controlling your situation, yes, which is never a good thing. Okay, So the difference between these two concepts is as such. Positive pressure ventilation is what we call the removal of smoke after the fire has been brought under control. Now, there's also a tactical approach called positive pressure attack, which means using the fan to improve the conditions for the attacking crew, which may seem crazy because we just said that, okay, but it's the air that creates heat. So how can we add air and hope for the better? Okay, there's a trick in that as well, and it comes in, and it is based on the understanding of um, of the principles. Again, coming from Firefighter Safety Research Institute. Now we have the modern fire curve, which is the blue one, and then we have comparison with the curve that is fire but with positive pressure attack, which is green. We see that the PPA, positive pressure attack, starts, and it first of all creates an increase of heat release rate, increase of intensity of the fire. But soon after, it works to remove large amounts of smoke. And we have to remember that approximately 2/3 of heat inside the structure fire are transferred by convection. So they are transferred by hot smoke. So if we remove that smoke, we remove a lot of heat. We make a lot of visibility, and we have great window of opportunity, the great chance to attack the fire. But in order to be able to do that, we must be ready, we must train, and we must have very good coordination. Now, if we don't suppress the fire, okay, the fire will go back and start creating even more heat and smoke, and the building is lost. Now, we don't want to do that. So it takes a great deal of practice and understanding, but once you understand and practice, it's a very powerful tactical approach, the positive pressure attack. Just remember that you have to have sufficient area of outlet openings. Now, not this. Again, coming from scientific research, we have a research from National Institutes of Standard and Technology, which is comparing positive pressure ventilation or attack with natural ventilation. And we see that initially there's an increase in heat release rate, but compared to natural ventilation, but in a matter of some seconds, we go over a peak and it's starting to fall down, and it's coming below the level compared to the natural ventilation. So there is definitely window of opportunity, and there is advantage in this tactical approach. Again, it requires a lot of practice. Okay, with PPV, what's actually happening inside? There's another research from Dr. Ezekoye from the United States, from the National Institutes of Standard and Technology, and so on. On this graphic, the color represents velocity of air. We see that there's a visible path of movement, but it's not the case that everything is moving. There's turbulence, there's acceleration at narrow points, at turn points, but majority of the structure is characterized with very low velocities of air or smoke, for that matter. So it's not the case that we are doing a lot of chaos inside. Okay, there's chaos and there's mixing, and along this path, when we go back to the idea of flammability limits, we are mixing air with fuel, so there will be flammable mixtures. If they can ignite, well, that's always a matter of probability and chance, but we have to remember that we are cooling down the atmosphere by adding cold air. But of course, there can be potential for trouble, but only if we are not understanding what we're doing, if we're not ready with extinguishing lines, if we're not providing the proper outlet area, surface area, and so on. Okay, so let's talk about the ratio. Now in this case, if you compare it to the previous, it's outlet to inlet ratio, and it's coming from a great book from Stefan Svensson, first book, and very recently, also second edition at MSB, Swedish Fire Rescue Services. Both are available in PDF. Great, absolutely fantastic, best quality knowledge from our dear Swedish colleagues. Okay, now I'm going to kill you with science. It looks terrible, but let me explain to you, and you will see that it's not terrible at all, and it's actually makes sense. So we see now, let me go back, just see this red line, and on this next graph, the red line is actually represented in blue, and the red line on this one represents something else. Now let me explain. Okay, efficiency of flow rate is pictured in this drawing in blue color. It means what is the effect in relation to the effort. This is exactly what is understood in physics by efficiency of any process. It's not measured by any means, it's measured basically in percent. What is the percentage of my success? If I'm making a lot of effort but I don't have a lot of result, my efficiency is low. If I'm making a certain amount of effort and my result is relatively high, my efficiency is big. Now, by using some equations, if you want to follow them, then I recommend to you that you go to Stefan Svensson's book. By using some equations, we can understand some very simple principles. Below the graph, you have an average door, average window. So they both have some area. We know that the efficiency of my positive pressure ventilation is depending on the ratio between these two areas. So I made this a lot simpler by adding some lines, vertical lines, that represent situations when we ventilate one window, two windows, three windows, four windows, five windows, and six windows. You can see this on the upper part. And then there's always one door, because it's the most common principle that we use the door as inlet and a number of windows as the outlet. Okay, but also an important part in positive pressure ventilation is pressure inside the compartment. The pressure is here pictured by the red line. And you see that approximately between 2 windows per door and 4 windows per door, there's an area of average conditions, which means that we are already working with decent efficiency and not so bad pressure. Why is pressure important? Pressure is important because if you have low pressure, even at high efficiency, your positive pressure ventilation can be easily disrupted by wind. And as I mentioned, wind is always a very important factor in all ventilation. Now, if you imagine a situation where you remove an entire wall from your room, an entire wall, which means that your outlet is great, maybe 6 windows, then you understand that whatever you put inside is immediately exiting the structure. But there's no pressure at all, basically because there's no resistance of flow. Yes, just like with water, if you put water through hose lines, if you have resistance, then you're losing your efficiency to transport water. Okay. So if we understand that, let's analyze some situations. Now we have situation A, very similar to what I've shown you in the first part. Okay, there's one window, there's one door, so our efficiency is not very big, but we have decent pressure. The pressure is 80% of the pressure in the inlet, which is a lot. So there's a great pressure buildup, and even if it may take longer, our ventilation is very powerful, and we cannot be easily disrupted by any external means, any external force. We move to situation B. Now our efficiency has increased, which means that we will be able to much faster remove smoke. But two important factors are the following. First of all, the pressure is significantly lower, so it's more likely that we can be interrupted by wind, and also it's in practical terms, the situation presented in this B example means that we are using multiple windows. Some of them may be outside of the burning room or burning area. It means that the hot smoke and possibly also flames will travel to that location. It can spread flame, it can spread fire, and maybe also it is a side of the building that is impacted by wind. So we have to remember. We move to point C, we make the situation even more towards that extreme, and we see now that our efficiency is great, but our pressure is very poor. Now it's very likely that it will be disrupted by any external wind, but also we can see that we may cause the flow to go to different parts of the building. I've also pictured another example that is coming from my own experience from exercises in an abandoned block of flats. We put a fan in front of the building, and we put a fan in front of the apartment. So we create a very large flow, and the flow was such that, first of all, the room on fire only had one window, so the fire was traveling with smoke, with flames toward another room with another window, but also because the pressure was too much, we had two powerful fans. There was not enough possibility for the entire smoke and flame and gases to be ejected through two windows, so we experienced some backflowing of smoke to the staircase. And when we have smoke in the staircase, it is always bad, and it's something that every firefighter knows. So if we want to use series of fans, we have to understand that every fan creates some buildup of pressure, and we have to understand where exactly do we want this buildup of pressure. Now we have three situations. We put one fan behind another fan. Okay, they both increase the pressure, and they work like so. Then we put them in a V position, so we position them like that. It's more efficient because we are not only directing two flows from two fans inside the structure, but we are also using the Venturi effect, so we are adding air. But if we want to make sure that we have enough of pressure, we can put the fan directly in front of the ventilated structure, like on the case on the right, where we are putting the fan inside of in front of the apartment. We only have to make sure that we don't cause too much of too much flow, and we have sufficient outlet surface. Okay. Now, also, we have to remember that if we put the fan in front of the flat or apartment, or even at the staircase, we have to make sure that the smoke is not creating a problem for our second fan, because we have an idea in our minds, we base the tactic on this idea, and this idea cannot fail. So we have to understand that when there's smoke, petrol engine will not work. So recent years have shown great development in battery fans. The battery fan that I showed to you for negative pressure ventilation, either by suspension in the passage or either by extraction of smoke from the window of the basement, just in the beginning of the second part of my presentation. These are the fans that are not influenced by smoke at all. Now, up to recent time, the disadvantage was that they are not as powerful as petrol-driven fans. This year, in the beginning of this year, we saw one manufacturer releasing a fan that is already as powerful on battery, and it's also important that it's on battery, not on the cable, as powerful as smaller petrol-driven fans. So it is my impression, or rather it's my conviction, I'm quite convinced that we will see further development of the segment of battery-driven fans, and I strongly believe that they will, with time, push to the side petrol-driven units, because petrol-driven units are heavier, usually heavier. They make more noise. They are louder, and they also produce carbon monoxide, as we just mentioned a couple slides before. So pay attention to the battery-driven fan market, because it is my strong feeling that it will be the new technology. Just like with any other segment in the fire brigade, we are saying about uh, electric tools for extrication, or even better and better lighting for the fire scene when there's night, when there's not enough light. We are getting more and more useful lighting equipment as well. So yeah. When we speak about tactics and tactical approach, we also have to understand that our advantage comes from some plan, and this plan can be introduced in stages. It doesn't have to be everything at the same time. So this concept is called sequential ventilation, and it is another example of how tactics are used to the advantage of the firefighting response. On this slide, we see ABCD situations, and we are seeing that the fire room was isolated from the rest of the structure. Perhaps there was a situation where we had a report of trapped victim, and firefighters were able to easily isolate the fire room, maybe attack the fire room through the window, and they used the fan to clear the smoke from remaining parts. So first, room number 1 with open window, then we see the window was closed. Room number 2, open window, window closed. Drawing number with the letter C, third room with open window, and then okay, the victim was found, and then they proceeded to put out the fire. Well, it's one of the possibilities. It can also be the other way around. First, the attack was made on the fire, and then one after another rooms were cleared. What is important here is coming back to the principle of efficiency and pressure. It's not every room at the same time, it's some sequence of rooms. So the choice is always in the hands and in the mind of the incident commander, because we have to rely on the reconnaissance, on the size up, which is always at the scene, at the time of the incident. So we cannot say definitely ABCD should be the case, or BCDA, or whatever else. We should say, look at the possibilities and not always make linear decisions. Understand that your tools and your training and your people are your resources, and your reconnaissance, your knowledge, your experience are your resources, and play with those to your advantage. Then again, you are using the very definition of tactical ventilation. Okay, staying with tactics, we also have to understand that since we are now in the era of plastic materials, of synthetic fuels, we have to have a very clearly defined purpose for any kind of ventilation. So there are three major reasons to ventilate. Okay, first is vent for life, which means you have trapped victims. You have to get to your victims as quickly as possible, because the longer they are staying from in smoke without breathing protection, which is always the case, the more toxic substances they will take into their bodies, and they are more likely to suffer or die in that fire. So ventilation for life. In general, for the commander, he understands that he is making that decision to gain access, or to facilitate, make easier search for victims. But with positive pressure ventilation, which is, as I mentioned, one of many ways of making tactical ventilation, it's ventilation of smoked areas far or close to the seat of the fire, conducted to make sure that the fastest possible access to trapped victims is made. And again, we just covered the topic of sequential ventilation. It's a great way of making positive pressure ventilation work for vent for life principle. Then similar principle, but okay, slightly different. It all may seem very similar, but again, there may not be a victim, or they may be a victim, but not directly threatened by smoke. So we are venting for fire. So our reason is to improve the conditions of working inside by lowering heat and improving visibility. So when we use positive pressure ventilation for that, again, we are using the fan to push air inside and displace the smoke with clean air. And this is the way we do it with PPV. And also vent for safety. Just when we want to improve the safety of firefighters in different ways, we can make ventilation, and when we are talking about positive pressure ventilation with fans, it's made by either sequentially ventilating, because safety is visibility, safety is temperature. We understand as firefighters that if we see more, we are less likely to get in trouble, like fall inside the hole in the floor, or lose our partner, contact with our partner, or anything else, or stay in hot area. We can, instead of staying in hot smoke, we can work in clear air, and so on. And so with positive pressure, we are doing this in order to remove smoke and increase safety of working. So if we have a situation where we have a fire, and there's smoke coming into an adjacent room, and there's a possibility or tendency, possibility or probability, that's what I want to say, of ignition and propagation of flame, which always increases the pressure. Over here on this drawing, it's characterized by the plus signs. So in such a case, we can either ventilate in a gravitational manner. So we lift the smoke by opening a high window or cutting a hole in the roof or opening a hatch in the roof or whatever kind of opening that we make in a high portion of the building will serve to that purpose. And or we can use the fan with overpressure and stop the inflow of the smoke to that area. These drawings are coming from a great book, again, from our Swedish colleagues, which is called Enclosure Fires. Again, please make your Google search and you will be able to find a PDF. There's a great deal of knowledge that our Swedish colleagues are providing us with their books. Now we will move to some final stages of the presentation when we will discuss some of the findings from the International Fire Instructors Workshop. Some impressions from that workshop are here. And we had our great colleague Arturo Arnalic visiting us from Spain, and we made some live tests with live fire tests with temperature measurements on what he calls the 3T technique, or combined fire attack. 3T stands for tools, techniques, and tactics. It is not always that we have to stick to whatever was our usual traditional way of fighting fires. Back in the days, we did not have spray nozzles, we only had straight stream nozzles, and we fought with that. So the tendency was not to use water at all, but only when you saw the flame. Only then the firefighters were using water. Then in the 70s in Sweden, Christer Giselson, Mats Rosander were the two pioneers that said, hey, but smoke is fuel. It burns just like other flammable gases like LPG or something else. So we should use our water in spray form, in mist form to decrease the risk, to dilute the gas, to cool down the gas, to introduce fog, to introduce an extinguishing agent, which is water steam, and by this make our safety greater. Okay, so this was traditional smoke diving, so diving into the smoke with low visibility, searching on knees and so on. Then we forgot a little bit about the tactic that was used, which was called transitional fire attack, which means that there was a attack from the outside through the window and transition into the inside. So first, initial water was applied from the outside. Then, as I mentioned, in the 90s, the fans were introduced, and the fans were used to the fans were used to remove smoke, but then they also have the tendency to make the fire bigger, so also proper tactics had to be used. So but what Arturo was trying to tell us is that you can use selected elements of those different tactical approaches in order to be able to get the best result. So for example, we see a fire here, it's a bi-directional flow in the window, so we understand that the smoke is not spreading to the staircase. Let's remove that. Okay, so we have firefighters applying water from the outside, which is called softening the fire, or exactly as I mentioned, transitional attack. For this, of course, we need two teams. One is on the outside, the other is on the inside. They coordinate. So once the team which is applying water from the outside makes good effect, and it usually takes 10 to 15 seconds if they are able to reach the window with their water stream, then they coordinate and they stop their application of water, and the inside team is making progress through the door. At the same time, the outside team can use positive pressure ventilation for two purposes. One is creating overpressure in the staircase in order to prevent any smoke travel to the staircase, and the second is to remove all the smoke and all the steam created by extinguishing water in favor of the advancing team. And then as they continue, they win space, and they are able to rescue the victims faster and so on. So it's one example of combining different tools, techniques, and tactics for the benefit, and whatever is possible, because not always every action is possible. For example, we cannot always apply water from the outside. For example, if the fire is on a higher floor, if it's 20 meters, then we are starting to experience problems with reach from the ground. 20 meters is 3 times 7 is, sorry, 20 meters, 21 is 3 times 7. So 3 meters per floor, 7 floors. So if it's above the ground floor plus 6 floors, then we have to understand that maybe not every water stream can reach that. For example, high pressure streams from hose reels, from small diameter hoses, cannot always reach high places like that, and also they will be disrupted by wind again more easily. Okay. We will now move to also flow path management. I'm very proud of this picture because I'm surrounded by firefighting legends here, but I want to tell you that from left to right we see Mats Rosander, who again was creating modern firefighting techniques in the 70s in Sweden, and many countries from around the world, not only from Europe, traveled to Sweden to teach from the Swedes. They're absolutely revolutionizing techniques. Then it's my humble self. Then we see Jens Stiegel from Germany, who's a fire chief in Frankfurt Fire School. Then we see Michael Reich, Dr. Michael Reich from Germany, who created the smoke curtain, about which I will shortly speak. And then we have Joe Starnes from the United States of America, who was one of the founders of the project called Kill the Flashover. And they worked a lot with the flow path management, thermal imaging cameras, and agents that you can add to water to improve water's effectiveness. Okay, so the idea is simple but genius. You have a curtain that is easily placed in your opening, and by doing so, you're blocking the upper part, so you're influencing the smoke exchange in your fire. Dr. Reich made numerous fire simulations like the one you see on the right, and he understood that if you can make on the left. And he understood that if you can make a device that will block the upper part of the window, you are creating a lot of advantage for yourself, for your firefighting. Here we see the smoke curtain as seen from the inside, from a basement fire. It serves greatly to block the upper part, which in turn translates into better ability to keep the staircase free from smoke, which again is a major tactical factor. Okay, so this graphic shows why exactly this device works like that. We have a staircase, there's a fire on the first floor, there's some smoke, and we have to pay attention to the edges, to the limits of the openings. So on red, with the red color, we see the edges of the window, and with the blue we see the edges of the door, and plus the curtain we see with the black color. So what I'm trying to present here is the following. If you look at the top part of the window, it's usually higher, situated in a higher place than the top part of the door, which means that the smoke will first exit the window, and if there's a lot of smoke and still the layer will be growing, then it will also start leaving by the door, under the edge of the door. Now, if you look at next edge, the lower edge of the window, you will see that it's more or less halfway in the height of the door. Now, if you can place an object that does not allow for the smoke to leave through this height of the room, and this object is exactly the smoke curtain, it was designed to do so, but at the same time you keep a little bit of uh, accessibility in the lower part of the door. This accessibility is first of all for firefighters to enter, but secondly for very much limited amount of air to travel inside, because whatever air will travel inside will make a small clearance for you also and create some small visibility area near to the floor. And now you are creating a situation where by gravity, by natural flow, there is an income of air to the door and the outcome of smoke to the window. So basically you're helping in directing the smoke outside through the window and not through the door, because again, if you're directing smoke through the door, it's creating problems for you and for your evacuation. So it's a very simple concept, but has great potential for aiding, for improving any situation in tactical terms. Now we can see on next, okay, and then if you look at the bottom right part of the drawing, on the black you see flow of smoke, on blue you see the flow of air, and you see the difference in height and the overlap or the clearance, as I named it here. The clearance is what I understand by clearance is the difference between the levels, different levels of flow of smoke and flow of air. If the clearance is smaller, there's less interruption. So by this geometrical flat, but we can imagine this in 3D, but by this geometrical flat representation, we can understand why exactly this very simple device has such a great potential to work in favor of firefighters. So now that we have presented on numerous aspects of tactical ventilation, we can refer to a great book by Paul Grimwood again, and summarize the golden rules of tactical ventilation, as we can call them. We have to understand that every tactical action has to have a beginning, has to have a point from which we can begin. So closing down the structure until we achieve readiness is a good idea. If we don't know exactly what to do, anti-isolation, anti-ventilation, or isolation of fire will always buy us some time, or in majority of cases. Every door is a ventilation point, and we have to understand that once we open the door, we are starting to add air to the structure. So if we close the door, on the other hand, we will stop the growth and the intensification of the fire, or we will dramatically reduce it. We have to understand that, especially because the fires are now burning with artificial fuels, we have to always carefully plan. Every ventilation action has to be coordinated. So we can never create an opening that will place firefighters between the fire and the opening, because they will be in the outlet part, in the exhaust path. And that will most likely cause increased velocity of smoke movement, which has the tendency to put them in danger of health and even danger of life. We have to understand that the windward side, the side affected by wind, is a dangerous side of the building. We should never vent, which means create ventilation opening. We should never vent the windward side of the building, where firefighters or occupants may be on the leeward side, on the side of the under pressure, because again, we will place them between the fire and the outlet. If we are talking about positive pressure ventilation for tactical use, because most likely we will use this kind of ventilation, the vent outlet, or the total surface of numerous outlets that we can use, must be at least equal in size or larger than the inlet, but not too large, because we want to add effectiveness, but we don't want to lose pressure, which will be our safety factor. If there's a lot of fuel inside, if there's a dense fire loading, we have to understand that there may be only a limited time for firefighters to work inside that structure. And definitely, if you are suspecting or there's confirmed dense fire loading, well, we have to be very careful with ventilation, because we may easily lose with air access, actually, because we can easily lose control of that fire. And last but not least, if we're using positive pressure attack, before we are entering the fire, we should wait some seconds, like half a minute, 1 minute, to first of all direct the flow, secondly see the effects on fire and smoke, and understand if our actions are giving us success. Because if we go inside too early, prematurely, we can be surprised by the unwanted outcome. Okay, that's it. That wraps it up. Sadly, I have to finish now. Thank you for your attention, and if you have any questions, let me know. You can follow me on YouTube, on Twitter, and I have some pages on Facebook as well. But also there's my email here, and yeah, I hope you enjoyed it, and see you in the next presentation. Thank you very much.
Shimon, once again, thank you very much for a very interesting topic. Yes, we've touched this topic during the first edition of Baltic Fire Forum 2 years ago when we met live here. But still, this topic is so much unused and so interesting. Don't you say that?
Yeah, absolutely.
Yeah. So I think we shall just invite our national fire department also to this topic and to try this at our national fire ground, which will be very interesting to see. Next topic is about the fire extinguishing agents. This is also a very common, very important topic, especially after Alytus tire storage fire. We know that using fire agents or foams, it gives massive effectiveness on extinguishing a fire. So Simonas, on your previous job in a fire department, I've heard that there are some problems with using, let's say, foam during training drills. Is it true or not so much?
Yeah, that is true. Was Martinez, because we just like thinking about that foam. We know that it's most of one of the most how to say most effective extinguishing
Agent.
agent, but we a little bit like scary about that because of the price and ecological subjects. Yeah, so using that, I remember like in training we had like big drills in Vilnius.
Was it in Vilnius? Yeah,
Yeah,
I think I've heard about it. Yeah,
I remember one of the biggest in Vilnius. It's an oil station. So we were using that because of it's for that. It's for that. Oil, but not just for that. Like thinking and what we were learning from other countries in Europe or all the world. They're using the foam extinguishing just for everything.
For everything.
Even forest fires. Yeah. So.
But I've heard that in Germany there are lots of talks, especially from insurance companies, about the so-called ecological crisis after really big fires. Let's say not so long ago we had this Alytus tire storage fire. We had all the water was just drained out. We have a special also presentation about that. Paulius Grigaliūnas, Sveko Lietuva. He will also talk about the worry while extinguishing this city fire. But basically what we had was a really ecological crisis. I don't know, was there much foam or not, but basically for some amount, the weather, the air, and the underground water was totally filled with that.
There is a problem. We are, like I said, we are scared a little bit about using that foam because sometimes we don't know what we are using. It's friendly for nature or not friendly. So.
But in Vilnius, in Lithuania, let's say during your job, what fires did you extinguish with the foam? Let's say with totally just foam.
Yeah.
Just the cars? Would you say that, or something more?
Yeah, there is ways like one of the subjects in the fire is material. Maybe it's oil, fuel. We are using that because it's very effective, very effective. But I remember even using it the foam. Extinguishing fire in just like in building a house.
Okay.
Yeah. So
even so.
Yeah. So why not? I think the main thing we don't have to think just about price of them. We have to think about effectiveness and like we are talking nature friendly foam.
Yeah. I would say that, amen, brother, because it's really it's really true. And the next presenter is Kamil Marianek from company Fomax. He will talk about the compliance and practice in using the foams. So Kamil, the stage is yours. We are waiting for you.
Hello once again. Now we will speak about the compliance versus the best practice which we are having, because we need to consider that the standard is always few years later from the knowledge which we can have it from the fires. So we should apply first and fulfill all these compliance standards, laws, but we also need to consider the knowledge on the market as best practice and methodology and technology of Williams' product. So, what can go wrong? In a raffinery, seriously, everything can go wrong. Everything. There's even not one spot which is not in danger. All the crude oil refineries, petrochemicals, bases of crude oil are in really, really massive danger. And even if we locally in the Central Europe, if we are not having too many fires now currently, it's not that the prevention is working okay. No, it's just because there was not so many factors in one moment, which at the end are making a fire. And the fires, look what can happen. What is going on with the tank? Let's say that it's a 20,000 cubic meter crude oil tank. So it means that crude oil in this tank costs something like a 20 million US dollar, and the tank costs something like a 5 million. So it means that 25 million US dollar can fire, consumed, and then look what is happening. It's a lot of money. It's a lot of money. Insurers are not happy, and I can be sure that no one is having in his police in insurer that they are giving you back 100% of money. I would not believe that one. Look once again. If it's as we said, it was one tank. Here we can see the several tanks. Look this pictures really closely. Look how tough can be making action. Look how many streams of foam you can see here on the right side when there is one tank in dangerous, and there was several others which are also already burned. Boil over. Boil over. You know, in past, when I've been in study, I heard that the boil over throw distance, it's 3 dimensions of the tank. Unfortunately, my teacher was wrong. As I heard from Williams, and they give me certain refineries where it happens, it can be even, depends on the crude oil and amount of water which is in the tank, but it can be even 8 up to 10 dimensions. Look really closer, please, this picture. Look how many tanks has been destroyed. All refinery. You know how bad it is for this refinery? They can even bankrupt because of such a fire. How many years it will take to renovate it to the point zero before the fire? 3 years, 5 years, 6 years, depends how fast they can make a tender, and depends, do they have still money, or maybe fire has consumed such a crazy amount of money that they are not having a money now to renovate this. This can happen everywhere. So important is also in a good practice to not use the Rotterdam standard, where the tanks are crazy close to themselves. It's always good that if you are having at least 5, maybe 6 tanks in one area, and then we are having something like a 30, 40, 50 meters distance. But look, even if it will be 50 meters, if it will be boil over, we cannot do anything. So that's why it's so important to extinguish the first tank. First tank is the moment in which we will prevent all the refinery, or all the refinery will fall down. As look what happens in Pasadena, what happens in Bankfield. Bankfield is a crazy fire. It was in 2005. It was in UK, United Kingdom, and all the refinery has been destroyed. The action took days, and they didn't extinguish anything. They've been just only waiting, losing a lot of formation. They've been just only waiting when the crude oil will be finished. Look next one. As you can see also, here are the numbers. Here are the numbers, because we need to consider that if even one tank will be a bit destroyed but extinguished, okay, not okay. If it fall down because of the fire, okay. But look, the worst thing is if people are dying. I can imagine, as I am also a firefighter, municipal, I can imagine the situation in which I will die because I will just take small children from the home, if it's a fire, and I will give my oxygen mask to child and I will protect it, and then I will have some problems and maybe even I will die. But dying for crude oil, is there really thing which firefighters should make? This is the way of dying? What you will have on your gravel pit? You died because of crude oil? Guys, I don't want to have such a gravel pit. I think that you too. So what we should make it? Once again, this methodology, let's skip it to the next really dangerous pictures. Here we can see it was India in 2009, so not so long ago. 11 people, including 6 plant personnel, has been died. So what else we should say? Risk is high. Risk is high, but the bad and good thing is that we didn't have a big fire, massive fire in Central Europe over 15 years. So everyone is thinking, oh, there was no fire, especially the economics guy, the purchasing departments, they're always thinking about the numbers. So why we should buy for a 2 million euros equipment? Why this foam engine? Let's buy the cheapest one. This is the moment after 15 years where nobody remember how crazy situation is a tank fire. So that's why it's our job to learn the CEOs and all the managers which are deciding about spending the money, that this can happen also now in your refinery. And how you will be protected. We are sending you documents what you should buy. If you are not buying this, we just recommend you. I cannot do anything else. I can recommend you what you should have it to avoid such a situation. So as we can see, to understand the way we should go and prevent all our refineries in case of the fire. Oh, okay, we can just follow the standards, the law, but always I'm asking, please just prove me that someone use standard EN or local law and they, according to this law, extinguish a fire tank. Just please find for me one tank, but not small, few meters, one tank over 50 meters diameter, extinguish according to the rules which are in the local law. So as we can see, here are few types of the standards, codes, government affairs lobbying. So we can see that it's a code, it's a law, it's a standard. But please ask yourself, do you think that the guys who just made local law even saw the tank fire? Ask yourself, you want to only just fulfill the law? Or maybe you would like to extinguish a fire and don't have anybody died? It's your decision. And we can see what they are saying. So laws, it's always providing basics. In the basics, that the most important is evacuation and people. It's really good. Codes are always defining where and how you should, where you should have this system as required. And standards are defining how comply with the code. Look how many type of codes we are having all over the world. As a basic compliance, we can use NFPA or EN. Here is a British, but it depends on every country. EN 13565 it's in every country, so we can have it in every version. And there are just some kind of standards compliance which you can use, but there was no even single fire, in my opinion, extinguished by even according to an FPA standard. And why it wouldn't never happen? Because they are stating too low application rates. Application rates in NFPA wasn't being proved in a true fire within a big tank. No, it is only minimum, which you should have it, but don't go too far. You will never extinguish according to these application rates. Same will happen for a rim seam fire. Maybe for rim seam fire, they are good, as NFPA is good for a fixed installation. The standard is really good for fixed installation. They did many tests about it, and they proved that the densities, application rates are correct for fixed installation, but never for a mobile equipment. We can see here for our band fires how it should look like. Here we can see how looks this in the EN 13565. Also, they state for what type of the tank, for what dimension, what kind of equipment you can use with what kind of densities. But still, if you will look in the EN, they said that within tanks like we are now normally having in Europe above 80 meters, there is no practice. There's one practice, they state, that only Williams fire extinguished the biggest tank fire over the world. It was dimensioned 82 meters. 82 meters. It was Orion refinery. 82 meters they extinguished according to the methodology. Guess how long it took them extinguish 82 meters tank? They always claiming 65 minutes. They extinguish within 63 minutes. So look how close they have been, and they did success. After just only 15 minutes, they control a fire. So it means that the smokes and the flames has been really, really lower than it was before they start the action. Look what is happening when the surface of the tank and the band is in fire. So that's why we should consider that we need to locally feel the rules from the laws, maybe from local standards, if they are in government regulation standards. But we should always think what is the best practice. So that's why we should speak and share all the informations between us, because the best practice is always developing. It's never done fixed. Always developing. It's always changing. If you see other, if you are just going a bit right or left from the methodology, we are checking what is better. It's always a process, which is always, which will be never done 100%. It will be always running process. So that's why it's really important to share the information. How we can share the information like this conference. Like I am also inviting you for a training in the US, 1 week training, where 3 days we are on the territory of the refinery, which now it's not working, but we are using them for our fires. So you can see all the tank fires. We are extinguishing 20 meters tank fire within a band 40 by 40 meters. We are also extinguishing the 3 dimensions fire. It means that local fire from some kind of leakage from a pipe, how to extinguish properly. We are showing you what kind of equipment, how you should calculate it. So it means that after 1 week, you are coming with a knowledge. It's just destroying everything what you had earlier in my mind. Believe me, I am fire safety engineer, and after I went first time and I heard this knowledge, I said, "Oh my goodness, we have never heard about it, or we heard totally in the other way." But you know, I'm not a guy who is believing everything. But if they prove me that using this methodology and technology, they extinguish above 300 tanks fire within a 10, the biggest tank fires ever extinguished, it was according to their methodology. All the tanks from the 45 meters up to 82 meters has been, if they've been extinguished, they've been extinguished using our equipment, our foam agent, our methodology, and the guys has been trained in US how to use it properly. And also we are, even doesn't matter for us, it's Estonia, Lithuania, Czech Republic, Ukraine, Moldavia, Belarus, Lithuania, Estonia, doesn't matter for us. Europe is really small, so we can train you everywhere, locally, later, during making a big training, and then we are seeing, or you are doing everything okay. We are just auditing and giving you certificate if everything was okay. If anything is wrong, we are just writing that, okay, you should practice this better. We are showing you how to make it, and then we are coming back within the next year or next 2 years and checking is everything going okay. So it means that you are having a constant support from us. We are not leaving you later with the equipment. Look what is also important. We are only one company who is providing for you complete solution. What does it mean? That in the other way, you should buy monitor from one company, pump from the other company, from third company hoses, from foam agent from fourth company. And all these companies are making orders only monitors, orders only pumps, orders only foam agents, orders only hoses. So what does it mean? That they have no idea, the producer of foam agent in such a contract have no idea what type of monitor will be used. The producer of the pump has no idea what kind of monitor it will be used. So how they can make for you fixed system if one company is providing for you products from 4 or maybe more producers which have no idea about themselves? I don't want to be laboratory rabbit. If you want it, it's your decision. Let's skip to the next one. This is a look closer, please. Please look closer. What is on the slide? Thank you. And we see that it's apart from United States patent because methodology of footprint, it's patented. It means that the guy, Dwight Williams, using his experience, and he has a lot of experience as he's been firefighter in a refinery fire station many years, and it was close to Texas where they are having massive hurricanes. So it means that they had many fires and they never extinguished a fire within 40 meters or more. So that's why Les Williams with his son Dwight, they open their own company, Williams Fire Hazard Control, and the firefighters, it's utopia. It's like a utopia because firefighters build themselves equipment and the methodology, they develop methodology to extinguish at all the fires in the refineries in Texas or in Louisiana. How they are making? Everything is ready for the helicopter transport. And how they are successful and how good they are. They are so good that all the fires, when it's a fire, they are just calling Williams. Williams is having 4 monitors, 4 pumps, something like 100 tons of foam agent ready on their warehouse. They are transporting this really fastly by helicopters, and they are starting action everywhere. Doesn't matter where it's in Texas or Louisiana, they are starting action within less than 1 hour. So that's why if they prove themselves and they are earning money, because companies are just hiring them for a job. Job means a fire. We are calculating how much it will cost, and then they are going to extinguish. So they will never go and start extinguish a fire when they will wouldn't be sure 100% that they will extinguish it. Here we can see information about the biggest tank ever extinguished. It was Orion tank fire in 2001. It was a gasoline, 82 meters, really big fire. As we can see, they used two steams because of the amount which they should have. It was something like 50,000 liters per minute. That's why they used two monitors to extinguish. How do you define effective fire protection? Look, this drawing. You see, can we go a bit closer? Look, the tanks are going bigger and bigger. Every 5 years, the dimensions, it's going like a crazy. The biggest one now in Europe are having over 100 meters dimension. You see this on the right, on the bottom, you see this small hydrant. You see this small hydrant? You think that according to your local law, doesn't matter, or you will have 10 meters tank, 40 meters, 50 meters tank, 80 meters, 100 meters, but still according to your law, you need to have this one small hydrant every, 50 meters, 100 meters, depends on your law. You think that it's a good? What you can do with such a small hydrant? This hydrant is just showing what are stating for you local law, standards, maybe codes. This is not best practice because firefighters trained by us, I don't know for what they can use this hydrant. Maybe later after action to clean the cars, maybe. Oh, you see, now in yellow, you can see this hydrant. It's crazy, but that's how it looks like. We can say that, okay, we did everything according to law, but you are 100% sure as a firefighter that you would like to extinguish this fire only by this small hydrant? That's why we should forget about only fulfilling a law. Because if our tanks are growing, our hydrants also has to grow. This is a best practice. It's a high capacity manifolds by each you can have it something like a 20 or 25,000 liters per minute. So if you are having 6, you can have it 150,000 liters per minute. It's a really good and massive flow, which you can have it for a crazy big tanks. For normal in Europe to 80 meters, we just need like a 56,000 liters per minute. And guys, I will just show you one thing, how you can calculate it yourself, amount of the foam agent which you need to extinguish. Let's go together with me. Use your phone, open App Store or the shop, Play Shop. Open App Store, or as anyone is having Android, please write Williams Fire application. Checking, yeah. Here you can find it. It will be, if you write Williams Fire, there will be only one application. Please download it. I will do it together with you. And we will make small training. Okay, it's ready. It's installing. Okay, let's just open. And what we are having here, just please change from the metric, from the imperial to the metric, and what we can calculate. please put it foam calculator. Please put it foam calculator. There is a first information that the calculation are done if you are using if you are using our foam agent, really extra quality. The Thunderstorm 1x3 813. This is the best foam agent on the market. There is no better foam agent, never ever on the market. Please do consider that this small, maybe even pretty small, much smaller than EN standard flow rates you will always have if you are using high quality foam agent. If you are using not our foam agent, these calculations are not good. Ask your foam producer, foam deliver, for the application rates which you should use it with their foam agent, but do not use ours, because ours are built on a really best quality foam agent. So let's put it big tanks as we are having now in Europe. Let's put it, guys, the tank size 85 meters. 85 meters. Then please put 1%. And okay, just calculate, click it, calculate. And what is giving you this application? It shows you what should be the application density on the full surface. What is in square meters footage of surface. It's giving you also the full surface application rate. What is really important for you, because it's showing you how many monitors and pumps you should have it ready in the refinery. Also, you can see what is the flow rate of foam concentrate. Here it's crazy. It's for 1% over 500 liters per minute. So that's why it's really important foam logistic. About the foam logistic and the rest thing, I can go detail it. If you will meet in your company or in my company during a long one-day training for methodology, then we'll speak about details, and then I can share with you the informations. All the best knowledge you will always have, and the top trainings when you will buy from us equipment. Knowledge worth a lot. So okay, so you can see also the amount of the foam concentrate required to extinguish. What should be the amount of water which we have to use. So you can see here that this application is making for you all calculations. But always remember, it's always when you are using our foam agent together with our system and you are trained and prepared. Do not go direction that you are buying the cheapest everything from the market, because if you buy some kind of detergent and foam agent, simple or I don't know, cheap AFFF, 3 or 1%, or cheap ARC, no. According to EN 1568, our foam agent is extinguishing test fire within less than 1 minute. Other foam agents which are also having class 1 is if you are extinguishing within less than 3 minutes. They are extinguishing within 2 minutes, 2 minutes 30. What does it mean? If you are extinguishing within 1 minute and they are extinguishing within 2 minutes, it means that for action, your action, you should have it 2 times more foam agent as you are having from our calculation. That's how it looks like. So maybe even sometimes something what is more expensive, at the end it's cheaper. Let's go to the next slides. Okie dokie. So we can see closer how it is look. 28,000 liters per minute. We can have it from the one high capacity manifold, not hydrant, high capacity manifold. We should forget about the hydrants. Hydrants should be close to the roads where there are homes. But on the refineries, small hydrants, guys. Look what can happen with simple fire with a small dimension hydrant. Here we can see it was just only 3-inch hydrant. Small dimensions. Small dimensions, it's always when you are losing everything. Look. You know what it is? In the past, before the fire, here was the pumps fire room. This was pump station. You see the building? No, there is no building. You can see just only a bit inlets to the pump. We see the exhaust of the pump, and we see empty tank of gasoline. This what can happen, guys. This what can happen if we will not start our action with 1 hour. Look, learn from the history, from other fires which happen all over the world. Look, guys. You see these pictures? They are not pictures from movie, special effects. This is live. We need to remember one thing, that doesn't matter which kind of flow you are having locally, doesn't matter what kind of code standard you are having. If you are applying our methodology, mostly you are also fulfilling your local standards, and you are doing something a bit more than your local law. Why it's important? I think that everyone should consider them, why it's so important on the pictures which I showed earlier. So it's question to you guys. Or we want to have only fulfilling standard and local law or codes, and we are thinking that, okay, I am protected because I did everything according to law. But are you good protected? Ask in your country, who did your local standard and based on what? There was some fire. Later, they extinguished any fire according to this law. My methodology is proved. Over 300 tanks fires. Let's skip the other. You can see how step by step we should implement it and what we should take into consideration to prepare our emergency plan for big tank fires. So start with compliance fire protection requirements. What works and what does not work. It's also really important to check it, or you're having a lot of rocks in your manifolds or in your monitor nozzle. There are many things which can go wrong, so that's why you should check it I don't know, every 2-3 months, even making a training. Must be suitable for the facility hazards, fit for purpose. Yeah, it means that we should have it just only to feel this suitable solution. We should have it high capacity pump station and the big dimensions pipes all over the refinery. Or if we are not having, we should have it a big tank with water to which we can connect our pump, and then we can start it action from a mobile pump. Also, we should have learned from the past incidents and global reports. JOIF shared learning. Please check it. The JOIF. You can find a lot of information from the past fires and all the incidents. We should always checking every half a year what happens. We can search it in Google. Believe me that you have no idea how many records you will find it if you will just start searching for such a fires all over the world. And what we can see what also we have to use to have our system working properly and to have solution ready for our big tank fires. Always speaking about with the guys who are having knowledge. Knowledge is not knowledge from the book only. Knowledge is always from a case, from fires, from accidents, and speak with these guys, with engineers, risk managers, what they did before a fire, is it was good or not, on what they are adopting after the fire. This is really, really important. with building best practice in your refinery. Collateral efforts of the fire protection. We can see. Look. What else I should say? You want to have it in your refinery or crude oil base or gasoline base. If you want to have it such a situation, just use only a fire trucks. This is the worst thing which you can use when you are starting preparing your emergency plan. In good practice, when you are having good practice, you should not base firefighting action on the fire trucks. Fire trucks are for local fires, for 3D fires, for local fires. For a tank fire, cars, you can use it for bringing trailer with foam agent, but never use them as a pump. Never use the monitors, because you will go so close to the fire, it can be damaged, even if it wouldn't be flat over or boil over. All the plastics can melt really easily. So that's why we are never using crazy amount of the trucks and people close to the fire. Only 2 persons, it's maximum close to the fire. Rest should be hundreds of meters from the place. As using our pump, you can build foam and water pipe for a distance over 2 kilometers. 2 kilometers. And 2 kilometers from the monitor is a foam logistic with foam proportioning. There is a pump, and the hoses are for 2 kilometers. And if it's a constant wind, as I said, you should just set up using always a drone to see where you are exactly putting a foam on the surface. If you are properly making footprint, and it was on the previous slides, you can be sure that you will extinguish, and you can just say to those 2 firefighters to leave the fire monitor to go with much better distance from the tank than just only 100 or 80 meters. As we have to consider that with the high capacity monitors, like just only Ambassador, 22,000 liters per minute, or version with 30,000 liters per minute is giving you 125 up to 130 meters throw distance. It means that if your tank has 80 meters diameter, we are having 40 meters consuming. So it means that with a 125 meters throw distance, you can have it your monitor 65 meters from a tank. Not 5-6 meters or 10 meters, which you need to have it to put a foam on the surface, as we just spoke in the previous presentation. To fight, you will be 65 meters from this place, or even much higher distance if the wind is constant. We see how it's going crude oil tanks. Scenario 1. Burn, froth, explodes. When it's explosion, we are not having just only one tank in fire. And then, after explosion, domino effect is starting. If it's a domino effect, we should leave the place and wait just only in a really high distance from the place what will happen. Look, guys, this can also happen in your refinery. This is a spill and dyke bonfire. Look, this is the next scenario. Burn, explodes, release, and start domino effect once again. Are you 100% sure that you can avoid? It depends on the methodology and equipment that you are having. We can check it for you or your documentation, as because of this pandemic, COVID, it's tough to travel because every 2 weeks they are changing countries which we can enter, and also you are having same situation. We can check it for you just only by documents which you can send us on email. There will be later my details in a presentation, so please to contact me, and we can make it for you just only small as the beginning, small concept where you should be for the starting, and we will tell you or you are ready for fire or maybe you are not ready 100%. Thank you, guys.
Thank you very much, Kamil. Fire extinguishing agents, foam, is one of the most effective things here in this topic. And thank you once again for a very interesting description of all those crude oils and all the methodologies, which are very good to know and sometimes even better to repeat.
Oh, yeah.
Yeah. The next topic is virtual reality. So virtual reality, for me, it's a game. How about you, Simonas?
Yeah, truly, it's crazy thing.
Have you tried it? Have
I
you tried?
tried before 2 weeks our talk. Yeah, in the museum. I
In
tried
the
it,
museum.
Yeah.
Okay.
It's really crazy.
Did you fall down? Because I recently fell down.
Almost.
Almost. This is really tough thing. But okay. So for us, it's kind of a fun thing. But did you hear that virtual reality now it's used for even tactics and studying firefighting?
Yeah, truly sad. I just heard, but not tried. But yes, absolutely.
For me also, just hearing. But here we shall have a guest from Holland, Martin Bosman, who is actually making an education training for firefighters with help of virtual reality. So, wow, this is very cool for me, very new, but recently very trendy. The new thing really was that virtual reality recently is not only for firefighters itself to talk about tactics or how to extinguish this or that, but also for looking for reasons why there was a fire. Investigation.
Yeah, absolutely.
Exactly. How do you think? Would that be also good for police officers or just the National Fire Department?
Oh, it's really for National Department, true. For firefighters, yeah, for investigators, for firefighters, just for learning. I think the best way to learn is like in virtual reality,
not
virtual
reality.
Yeah.
Wow! So once again, it's really a surprise for me. But the innovations during a Baltic Fire Forum, the second edition, starts live now. So let's hear from Mr. Martin Bosman, right from Holland, Virtual Reality Support Center. Martin, the stage is yours.
Good day, everyone, and thank you for inviting me to give you a presentation about simulation and virtual reality for firefighter, police, and medical training. My name is Martijn Boosman from the VR Support Center in Europe, and in the coming about 45 minutes, I look forward to introducing you to a number of different solutions that use virtual reality simulation for training and educating emergency responders. Let me show you, give you a bit of background about myself first. So my background is in simulation. I've been involved in simulation for over 25 years. I have been the founder of a number of companies in the field of simulation training for fire and rescue training. And I am now very proud to be representing a number of very innovative companies from around the world. One of them from Australia, who creates a firefighter trainer, the Flame Trainer, which I'll show you, but also another company from the UK who have created a very good fire investigation training solution. My colleague Kaspers from Latvia unfortunately couldn't join in the presentation, but if you have any questions, don't hesitate to reach out to him. What I would like to do is to run you in this presentation through different simulation solutions that fit different parts of your learning cycle: education, training for skills, firefighting skills, for example, training for command, for incident command, and even the use of simulation for higher levels of command, so strategic commanders at the fire service, but also their political counterparts like the mayor or the heads of the other emergency services. My objective is to be as interactive as possible. I will be showing you videos. I will be showing you physical demonstrations. You are in my office in the Netherlands at the moment, where you can see it's filled up with virtual reality headsets and other simulation tools. So let's give it a start. The first example I want to talk about is education. So we are talking about education in a classroom setting, or we're talking about education using e-learning, for example. Classical education until now is very much aimed at a classroom setting, or people reading books, your recruits, or maybe your higher firefighters that need to do refresher training. The technology that is coming up that could also very well be used is 360 VR videos. 360 as in 360 degrees, being able to look around, and VR for virtual reality videos. As you can see on the images there, this is looking at videos using VR headsets. Headsets, glasses, big glasses that you can put on your head, and you can look around. Now on the images to the lower right corner, you can see that it's not only headsets that are used, but the simplest headset that you can think of is actually your own smartphone, because the technology of 360 video is designed in such a way that it can run on a smartphone. So you can look at it just by grabbing your smartphone and looking at it, or you can put your smartphone into what they call a cardboard headset. That is the brown image at the top. I will move my mouse. I think you can see that maybe. What are the advantages of using virtual reality 360 videos is that you can actually create videos of your own risk locations. For example, industry, petrochemical factories, or high-risk locations, high-rise buildings, or other locations that you want training in. Using the headsets or using your smartphones, you can allow your students to train anywhere they want. And by creating 360 videos instead of just a video on a screen, you allow people to actually interact with the environment. And I can't explain that. I'm going to show that to you. The following video is a video of someone looking into a headset, so having a headset on his or her head, and running through a video for a health and safety exercise inside a petrochemical plant. The objective of this small exercise is, while you are being given a task, in this case to repair a pump, you always have to be on the lookout for dangers around you. So the task for the student in this video, in this exercise, is make sure you always look around. The student enters the environment, and as you can see, the student can click on arrows and can walk around. Now, you are not hearing the audio at the moment, so I will explain what's going on. The lady has tasked you to go and pick up the tools together with your colleague there and repair a pump. Remember, the objective of this exercise is always look out for dangers. And maybe you've spotted it already. There is a box about to fall on your head. And what the student can do is he can point at that box with the pointer. And if he selects that, the colleague will actually react and say, wow, well spotted. If you forget to click on that, if you do not see that, the box will actually fall on the head of your colleague. So the key about the 360 video is it looks very real. You can look around. You can actually take decisions by answering multiple choice questions, and the outcomes of your decisions actually are wrong or right. And if they're wrong, you will see the consequences of your decisions immediately. Here, for example, if you did not check your surroundings well, you actually would have a camera falling on the head of your colleague and hurting him. I hope this makes it clear what 360 video can do for education. It's one example of simple virtual reality that is relatively low cost to create and very customizable to your own training location. Now I would like to go to the next step. The next step is using computer-generated virtual reality for skills training. So the big difference here is we are not looking at real videos anymore. We're looking at computer-generated videos. And the first example I'd like to give you is an example
mark on the door, and the door's not closed. So as an
of
investigator,
a
we
scenario.
know whose that footmark was, and we want to know.
I'll just
why
let
door's
the
in open
instructor
position.
talk for a second.
Again, I'm going to run through the scene fairly quickly, sorry, so you can see what we're looking for. So we open the door and enter the compartment. We check behind the door for evidence. We notice that the door latch is in the locked position, so there's a reason why this door has been forced. And we could check the damage on the other side of the door lock to see if it corresponds with that. And the door is slightly distorted as well. You can just see the shape of the door there. On the floor we've got a brick. And if you highlight the brick, what's the brick doing in the compartment? So that'd be worth trying to find out some information about that. And looking down the compartment, you can see that the majority of the fire damage is confined to that corner. There's a perfect burn pattern on the wall. And then the rest of it is really soot damaged and water damaged from what looks like the firefighters' activities when they came into the compartment. Electrical items to the left, again, we can examine them like we have in other scenes. Again, they're not involved in regards to being responsible to the fire. For the fire, they're just involved in the fire, they're heat damaged. Some glass on the floor to the right hand side, and we'd want to establish where that glass came from and why it's so far down the compartment.
So you think you may be looking at a real video of a real fire scene, but in fact you are not. You were looking at a computer-generated 3D virtual reality scenario of a fire scene. And the scene was created based on a real fire scene by taking thousands and thousands of photos and videos and turning them into a computer graphic. But the student in this skills training for fire investigation is actually walking around wearing a VR headset inside a computer-generated world and is able to look at things, pick up objects, and do a fire investigation scenario without having to go outside and burn something for real. This is a technology which comes from the UK, and it's widely used right now there for training. Let's go to another level of skills training, namely firefighter skills training. And before I explain more about it, I actually would like to show it to you. On the left, flame extinguisher, which is fire extinguishing training, and on the right, flame trainer, which is firefighting training. So I have them both set up right here for you, and I hope you can follow along. I am not able to share this screen with you, but I hope you can see it reasonably well. This is flame extinguisher. And flame extinguisher allows a student only with this headset and with a fake extinguisher to actually run a fire extinguisher exercise. So I'm grabbing my extinguisher here. I am going to select one of the scenarios here, for example, a sofa fire. It asks me to stand in the middle. I'm not going to do that because I will be right in front of your screen. As you can see, I have to select my extinguisher type. I can select between CO2 or powder or water, for example. And if I select by powder, I can actually start extinguishing. The extinguisher will be empty if I use it too long. And I have successfully extinguished this fire. I will just show you one other example. I'm going back to the lobby. Let's select, for example, a transport scenario, and I would like to have a car fire. And let's see, let me use the foam here. Probably this fire is much too big for me to extinguish using a simple extinguisher. And I will stop here and take it off. So an example of an extinguisher training using a Vive Focus headset. So the computer is inside here, and a simulated extinguisher so I can train step by step my extinguishing actions. Okay, so that was the flame extinguisher, but let's go to the flame trainer. And the flame trainer is a professional firefighter training equipment which consists of a virtual reality headset and a breathing apparatus backpack. It is actually a fake one because it has no air in it, but it has a computer in it. A real nozzle, which you'll see in a second, functions completely realistically. A hose reel right here, which actually will pull me back when I start using the flame trainer. A control iPad, which I will start a scenario with right now. And everything that you see is connected to the TV here. Let me make some space for myself. Let me gear up myself. I'll have to talk a bit louder so that you can follow along. All right, so if I put on the VR headset, you will see on the screen behind me, and I will try to keep out of the way what you actually, what the student sees. So as you can see, I'm looking at a fire on a port. I have my nozzle lying down here. And what I can do is I can actually, let me do a quick check if you're actually seeing me perfectly. Okay, I'll move over a bit. Very good. I can use my nozzle. And you can probably see it. If I pull it down, it pulls me back at rather a serious amount of power. Look at the fire coming out of the container. That is the smoke gas layer that is actually on fire. If I put a little bit of water on it, you'll notice that it cools and then the fire knocks down. I can move forward, put more water inside, and if I want, I can change it from jet beam, for example, to full fog. That was fast. So I used 81 liters and I used an attack time of 36 seconds there. What I will do is I will change the scenario and make it a little bit more difficult for myself. Okay, here we go. Bit difficult with my microphone on my head. Okay, here we go. As you can see, multi-vehicle fire in the back there. And I can actually jump there using what's called my teleport function. Let's go. And as you just saw, I can start fighting the fire. The key question, of course, is my priority here my Tesla, my electric Tesla, or should I maybe first do my reconnaissance and understand that my highest priority here is my tanker truck. And I could start using water to extinguish this, or I can decide to ask my colleague to change to foam. Now, I don't have a colleague in the office due to COVID restrictions, so I need to use my iPad to make the change. I just changed to foam. Okay, back. Here we go. And as you can see, the foam, of course, is also totally visible. The key here is, and I will explain that later on in the presentation, is that the smoke and fire are accurately calculated here. So the smoke, as you saw in the container, but in this case, for example, also, if I do not put enough coolant on, the car will maintain its heat, and eventually it will actually burn through the foam again. So I have to keep applying my foam layers on it. Oh, I already did it. Here we go. 339 liters. And you might have noticed it also says air usage. And I will show you what that means. You probably cannot read it from there. But in addition to the firefighting nozzle, the water or the foam, here you can also see that I can connect a full face mask, and the air usage is actually calculated. And this red thing is actually a heat vest. And the heat vest can heat the student up to about 80 degrees if you turn it up maximum. And that level actually generates a very noticeable heat in approaching the fire. Let me just show you one or two more examples. For example, remember this solution came from Australia, so of course they also have a Australian grass fire, or a bush fire in there, as they call it there. Oh, there he goes. And I know that this one is rather quick. Oh, here we go, works. Let me see if I can get it. The smoke will actually spread, the fire will actually spread. As you can see, I'll just let it go for a second. You can see it coming towards me rather quickly, and that, I can tell you, is typically what grass fires do. So, this is actually hard work. Oh, sorry for that. Okay, oh yeah, it's getting out of control on the other hand, as you can see. So I actually have to move there. And if you don't look out, it's actually gonna run away from you, and it's gonna threaten this whole house here. All right, I will stop here. I think you understand the options. Let me just give you a close-up of this for a second. So the key is that there is a large number of scenarios inside the system. You can set the amount of pressure on the pump. You can, for example, set the level of complexity. You can make it very hard for the student to extinguish the fire, or you can make it easier for the student to extinguish the fire. Okay, right. I hope that gave you a good picture on how virtual reality simulation can actually be used for firefighter training. As you can see, I'm out of breath a little bit. Let me go back to my presentation, and I will give you a little bit of background on the flame trainer. The interesting discussion about virtual reality used for firefighter skills training is it actually useful? How does it compare to hot fire training? And what is important is that virtual reality cannot replace hot fire training. Let me be more accurate in my answer. Virtual reality can never, that's my opinion and the opinion also of the designers of the flame system, who is actually a firefighter himself for many years, Dr. James Mullins, is that it cannot completely replace hot fire training, because real fire is almost impossible to simulate. However, what virtual reality can offer is the simulation of components that in real hot fire training may actually be very difficult to replicate. So it is possible to create virtual reality to be very realistic, maybe not how hot the fire is, but certainly realism in being able to go to a motor vehicle accident, onto a virtual ship, onto a virtual petrochemical plant, which in a hot fire container is very difficult or very expensive. Big advantage of virtual reality is it's environmentally friendly. If you still burn wood, virtual reality is zero emission. Wood is very much emission. Of course, compared to gas-powered props, there is much less problems with gas power, but they are expensive to operate. Key aspect of virtual reality training is it's healthier. No carcinogens, no risk to the health of the instructors or of the students. And it can be cost efficient, especially if you use it in combination with hot fire training. Let me dive in a second into the realism. If you want to create a realistic virtual reality firefighter skills training tool, you need 3 levels of realism. The firefighting should be realistic. The person inside the scene should feel immersed, it's called. She should feel really inside the scene. Of course, the smoke and fire need to behave realistically, and it needs to look real. If we look at the simulator that I just showed you, and looking at the firefighting realism, we've been using it in a lot of different training setups. Flame is in use in a lot of different countries at the moment. And we see everywhere that firefighters who put on a flame kit start being firefighter. This is one example. And this is sorry, I thought there was another video, but you can always ask us to show it. It was a video from Sweden where we could actually see the firefighter going low under the smoke layer to be able to attack the fire correctly. Feedback from, I would almost say, all users, it feels real. The second level of realism, of course, is smoke and fire. The key about flame is that smoke, gases, as well as the combustibles, not only in the gas layer, but also the physical combustibles, are calculated at temperature level and in relation to the amount of oxygen around. The extinguishing agents, foam and water, have a cooling or smothering effect on the foam, on the fire, so smothering on the fire, and they have a cooling effect on the temperature. You can see this in the behind the scene pictures of the flame calculator. So the smoke and fire, as well as the reaction to the suppressants, to this fire, to the water and foam, are very accurately calculated in flame, making it a very realistic training tool. Last but not least, realism. You have seen a little bit far away, but you've seen a number of examples using state-of-the-art 3D simulation, graphics, and gaming technology. The artists within the Flame team have actually managed to create very high realistic scenarios. And I really remember very well a feedback from a very experienced trainer in Sweden, Mr. Sune Funkvist, who basically said a hot fire container where there is a fire in the back corner and we say it is a kitchen is not a kitchen. It is a container and it's on fire. So although the smoke and the fire are real outside, inside the virtual reality, you can change scenarios. You can spend much more time, for example, on the aspects of doing a good reconnaissance, having a very good communication with your team as well as with your crew commander, for example. So the combination of hot fire and simulated fire seems to be an ideal combination to train recruits as well as to maintain the continued professional education of the higher levels. Last point that I don't want to forget is it's fun. I hope you saw it when I was using it. It's actually a fun way of training. Now, I realize firefighting is not fun, but the young generation that comes in, and thanks to the strongly improved and increased fire prevention measures throughout the world, they never see a fire until maybe a real big fire until their second or third year within when they've become a firefighter. If you look at crew commanders nowadays, they may not have seen a serious fire until their 5th or 10th year within their career. That's the feedback I've gotten. So entertaining learning, but also getting them experienced in firefighting response using simulation will support the knowledge level, not only of the young generations, but also of the experienced firefighters. I hope that gave you a good understanding and an idea of how virtual reality could actually support skills training at a firefighter level. Let me go as last point in my presentation to one step higher, crew command as well as strategic command. And what I would like to show you is XVR. XVR is a 3D simulation program which can run both on screens as well as in virtual reality headsets. And they are used worldwide for incident response training. And the video I'm going to show you right now is actually a video created by a very active user of XVR, which is the petrochemical company ADNOC of the United Arab Emirates. And they made a presentation video which basically shows all the aspects of using simulation for command level training.
Beautiful.
Just a short impression. What you saw on this video was a training center where there was one instructor with three students all having a look at the scene, at the same computer-generated incident scene in the petrochemical plant from their own point of view. So this is an example of a team exercise where multiple division commanders or battalion chiefs, or depending on what you call it in your country. So the sub-leaders of a large-scale incident can all be trained together to respond to a scenario. The XVR solution is mainly aimed, it is not firefighting skills training. It is command skills training, command level training. The last level I just want to give you an example about is crisis management training. Again, using the 3D virtual reality within XVR, but also using another module within XVR, which is designed to simulate, for example, social media, email, websites, news websites that can simulate governmental websites with information, and combined with the CCTV images coming from the 3D virtual reality scene, it gives the input that is necessary for the higher level commanders in the strategic decision-making positions to respond to really large-scale crises. The video which I'm about to show you is a video from Singapore Home Team Academy, who have created a simulated training command room for their joint operation, police, fire, and medical service. And you will see a wall where the simulated 3D CCTV cameras are running an exercise, are running a scenario, and the people sitting behind the computer screens are actually responding to the simulated emails, the simulated sit reps coming from the field, the simulated responses from the media, for example, or from the social media. The video is actually a video that was that ran on a news network in Singapore, so that's why I'm showing you the news release.
A simulation center that uses 3D technology to train officers to respond to emergencies was launched today. Authorities say the new virtual crisis center enhances training with realistic scenarios and helps cut down on manpower and logistics. Tan Se-Hui with this report.
Been attacked with casualties along Orchard Road in front of Ngee Ann City. Activate our red storm protocol.
These commanders are responding to a bomb explosion which was created using a virtual 3D simulator.
We had passerbys informing officers of an unattended bag. Info is positive.
And these are the instructors behind the various scenarios. And their job is to make exercises realistic and unpredictable by adding elements such as bombs and protesters.
The home team simulation system is able to simulate situations which may otherwise be difficult to recreate in actual setting.
So I may look like I'm playing a computer game, but far from that, this is a realistic simulation of a chemical agent attack. So I'm playing a ground officer and I'm telling the officers in the command post what exactly is happening on the ground in Orchard Road through this communication device.
The simulation system can create up to 15 different scenarios. Currently, it can map out 4 areas: Bishan, Little India, Marina Bay Sands, and Orchard Road. Up to 20 officers at a time can be trained using the system, and exercises have been held since the start of the year. The simulation system will not replace ground deployment exercises, but will supplement them and serve as additional training. Home Affairs and Law.
So that last example was an example where simulation was actually used for the highest levels of command. And what you may have heard during the video also was that it used custom 3D environments of pieces of Singapore. It goes outside of this presentation to go into that level of detail about simulation, but recreating your own environments is a very expensive matter. So many users do not have their own 3D environments, but have a generic piece of city or a generic highway or a generic petrochemical plant to train. And most instructors actually see that as being extremely effective. I hope in this presentation I've been able to give you a good overview of different ways 3D virtual reality simulation is being used, from education into skills training into command training, and even into very senior management training. All of the examples I gave you are in use. That is, it is nothing new. It is innovative. It is constantly being improved, but all of the solutions I showed are actively being used around the world for education and training. And if you have any questions in implementing it or using it or trialing it, please do not hesitate to contact us. My contact information and my Latvian colleague Kaspars Gorilov's contact information is down there. I thank you for your attention, and I'll be glad to answer any questions you have.
Thank you very much, Martin. Virtual reality now is not only a game for me,
truly.
education also. Military things, militaries are also using these kinds of virtual reality. I do understand you know something about it.
Yeah, we absolutely not using tanks like helicopters, not, but yeah. Yeah, military, I think tactics and technologies is more steps
more advanced.
more advanced, like in a firefighters world. So we have common drills. We saw like their reality, like they are learning. So we are learning from them.
It's interesting. I mean, this cooperation between firefighters and military is always a big challenge for everyone, or especially when you talk about civil defense and not just the usual fires. But this is really good. Martin, once again, very, very interesting topic. Thank you. And I hope that finally in Lithuania, we also have this virtual reality room. Because basically, the Virtual Reality Support Center has its own branch in Latvia. So not so far for us to have a training. And but hopefully we shall also have this kind of virtual reality trainings here, like common thing in Lithuania. Why are we talking about? Probably the viewers are asking the military things and this compliance. Everything about is robotics. Robotics is the topics which are very much into recently, especially after the famous and very sad Notre Dame fire. So probably you remember this tragic event.
Truly disaster. Yes.
One of the things that really caught my eye was the French Paris Brigade using a robot for extinguishing. Can you comment something on that?
Yeah, I don't know a lot about organization of fire system in France, but if it's like the part of organization, like robotics, so truly amazing. Wow. Nice.
Yeah. Why did they use it at all? I mean, some people were asking about the helicopters and dropping the water from up.
I think for a safety, Martinez, just for firefighter safety. Yeah.
Okay.
It's really good.
Okay, but the question, from my side, in Lithuania, we do not have Notre Dame. Okay, we have smaller churches, but nevertheless, we have forests. I saw in our sponsors Milram video that it can do such even things, but I couldn't imagine how deep it can go into the burning forests. Is it possible?
Talking about churches a little bit, yeah, we had maybe not Notre Dame, but we had Titovene or smaller fires. I think the robotics or drones, it's not like future. It's reality.
It's reality.
A lot of organizations are using them, including military. Yes. So why we are not using them? I don't know. Yeah. So
I can see that now. Some things that we thought that are the future are basically the reality, and nowadays sometimes we just keep on, the Baltic region that we waiting for news to come.
Yeah.
But basically, the Baltic Fire Forum is a platform for us to also ask loudly and say that we want to be in the same level as all the Western countries and have the same equipment technique?
And talking about forests, already it's used. Drones, robots, in Europe and United States of America. It's going.
I think
nowadays.
It's also the satellites, was it?
Yeah, they are using satellites just for monitoring because fires in the forest. It's already big problem not in United States of America, Russia, and it's like a problem of all the world. About climate change and all those things. So they are monitoring just the
area and
the area, and it's not going like fire is in going already. No, just for monitoring, for starting, and just flow there and keep
really interesting. Okay, this is good. So once again, probably the viewers are giving themselves questions, military, civil defense, firefighting, what is it about? I think what it is about is the Milrem company, Estonia. Mr. Remo Ojeste will tell us about the using of robotics for firefighters in different situations, really different situations, and it's not the future, it's actually today. So, Remo, the stage is yours. We are very, very much waiting for your presentation.
So, hello, I'm Remo Ojaste, the Regional Sales Manager in Milrem Robotics. Before we get into the main presentation, I would like to take a moment and thank all the first responders who do the job and keep us all safe every day. I believe that our innovative solutions are able to significantly reduce the risk of frontline troops and the first responders. It is a dangerous world to live in, and by implementing technologies, the risk could be lower for sure. So, what are we going to talk about? Why robots? We talk about a little bit about Milrem Robotics, our products and services, our rescue product line and concepts. We go more in depth into the rescue UGV. We also go over some first-hand experiences and possible use cases that we have gathered, and then we're going to sum it up. So, why robots? As we know from our day-to-day lives, humans get bored easily, and we need exciting things to do, so we won't get bored. But robots, on the other hand, you can give them as boring task as you can, but they will still not get bored at all. Also, we are born with different senses: seeing, hearing, smelling, touching. Unfortunately, all of those senses are limited, and we may not be as effective in all environments as the robots are. But robots, for example, can use different type of electronical, optical sensors to identify and detect objects from longer distances. And there's also a possibility to do that in other spectrums that are going beyond human capability. So we can say that robot senses have close to no limitations, and the only limitations that there are sometimes our imagination. Also, almost everyone knows some people that are really strong and some people that are really fast. For example, Usain Bolt, the first fastest man, but when we compare him to robots, it's quite everyone understands that in a matter of 100 meters, the person will get tired, but robots can go on for days and even for weeks. without getting any fatigue. Also, it's very hard to focus by human. I think every one of us have been in a driving with kids around, and it's very distracting when your main job is to stay focused on the road. But still, sometimes they grab your attention. When you take a robot, for instance, they will never get distracted. Nothing and no one can distract them. So humans are also not perfect, and we are flawed, and that's actually something that makes us unique and interesting. So, but robots, they can be perfect. They can do repetitive, boring jobs, and they can be perfect in their execution. So 100 times out of 100 times, for example. Also, the environment affects us significantly. So robots can work in environments where it's too hot, too cold, there is a radiation environment going on. So robots can outperform humans in many other aspects. So this opens new possibilities and capabilities that have not been possible so far. So, for example, Milrem's main focus has always been the military side, and we are that's been our main effort. But and we are one of the leading manufacturers in UGVs in Europe. But we have also similarities in other fields, and definitely rescue and military worlds, they mirror each other. So we also need to take people out of harm's way in the military scenarios, gather timely and relevant information, and just to make better decisions. And we are pretty much operating in hostile and inhuman environments. The main focus in all of those aspects is still to bring human out alive. So saving humans is critical in all of those scenarios. A few words about Milrem. So our mission is to provide innovative robotic solutions for challenging environments. We believe that our cutting-edge robotic solutions fulfill a higher purpose, enable more meaningful lives. So we are located in Estonia, our HQ, and we got established in 2013. We have 3 offices. Two in Estonia, one in Tallinn, and one in Sweden. Also, we have over 100 people, and out of those, 80% of those people are actually engineers. And our first UGVs was developed in 2014, and our first iPad 2015. And in 2019, we released our first rescue product line. So our customer portfolio. So we have mainly been we mainly have military clients. So NATO countries, 7 of them, and also in Asia, we have few countries that are our clients. So our main products, we have mainly military products. So our number 1 product is a hybrid infantry system, or you can call it THEMIS. First hybrid full modular unmanned ground vehicle in the world. The vehicle is intended to provide support for dismounted troops. Our second product is multiscope. It's a UGV combined with know-how that's collected from extensive testing from the THEMIS and is now implemented in the civilian sector. We also have a much bigger platform compared to THEMIS, which is like a size of a tank, kind of. And it's intended to support mechanized units and act as a wingman to main battle tanks. We also have a intelligent functions kit, which pretty much is a package that includes the necessary hardware and software to modify any vehicle to give it control and safety functionality. And the last I want to put emphasis on is that we need to put different type of systems together, and we are always specializing in that. For example, when you take Themis, you want to insert a different type of platform and want to work it together with troops, then it's 3 different systems that need to be working together, and that's something that we are doing as well. So now let's go deeper into the rescue field. So our main main partners in the rescue field have been Estonian Rescue Board, whose input has been undescribably valuable for us, and also widely recognized experts in distinguishing fires, and our payload provider, Innofoam from Netherlands. So here our main platform, so the multiscope, and now we will go see how it's built up and what it does. So it's a diesel electric hybrid. It has 2 electric motors located in the front of the track. The vehicle uses always electric motors for driving. It has a battery block, and the diesel engine on the right side is continuously charging the batteries. So the runtime for this hybrid solution is up to 15 hours. Now you will see a video of the capabilities of the UGV on a terrain. So let's now unpack a little bit what you saw. So as you can see, the vehicle is really capable. It can drive up to 20 kilometers per hour, and maximum towing speed is also quite high. Even if it, due to its small weight, it has a lot of different advantages. The nominal payload is 750 kilograms, and all the specs will remain achievable with that. However, the maximum payload is 1.2 tons. It can cross water obstacles as deep as 60 centimeters. And as you saw on the video, we have tested in Mali deployment where we pulled a 32-ton armored vehicle. And also due to its tracks, it's very low ground pressure. Also, it's another aspect that's very important to understand is that it's modular architecture and design. The center form is adjustable, so the ground clearance is adjustable, and the only thing actually connecting 2 modules is a cable, and there is no mechanical connection between the central platform, and that enables us to customize the measurements of the vehicle as needed for the customer. Also, another cool thing is that you can add different type of payloads and increase the capabilities. So, for example, you can add fire monitors with different power supply, and you can replace that with a water tank, for example, with a fire monitor. Also very helpful for the firefighters would be a hose laying system, and also a system that you can carry, collect it. And picture you can see the additional hub for tethered drone for having, for example, 80-meter high observation point, or to relay radio communication. So the flight time for drone is basically unlimited due to the tethered version. Also, it's really easily interchangeable. So you can, it only takes 5 to 10 minutes, depending on the procedure, just to release it and put the new payload on. So taking all of those things into consideration, you can see that there are a lot of different type of options, and this is the kind of product family we are dealing with at the moment. And in the middle is the furthest one, called Hydra. So here you can see a picture from quite some time back, and also another possibility is that you can improvise and use handmade solutions. So these pictures have actually taken from Estonian Defense military polygon, where there is an area that was too dangerous to be on foot, because there was unexploded ordnances laying down everywhere. So the solution was that firefighters, they used a little bit of duct tape, and they put the fire monitor, attached it together, and that worked as well. So, but during this time, we have evolved a lot from duct tape, and we actually have a real solution right now, and it's called Hydra. We will go and look a bit deeper inside that as well. So first, we're going to talk about the fire monitor. So it can supply up to 3,000 liters per minute, but it's adjustable. You can change the fire monitors to lower ones and to bigger ones if needed. It has a 360-degree maneuverability. It's radio controlled, and it can use water and also foam. And it, depending on the pressure of the water, you can extend the water length or throw length up to 62 meters. But if you change the fire monitor to the more powerful one, the throw length can be even further. So now let's look at the bottom part of the Hydra, so the skid unit. In front, you can see there are two sprinklers, which are meant for cooling down the front side of the vehicle. In the middle is the control unit that is made for that does all the decisions between the radio and the fire monitors. There are 4 fire hose compartments, 4 hose connectors. In the front, there is expansion generators for grading a foam blanket, and also there is an extra light source just to give some extra lighting on the scene. It's also easily transportable, and due to its small weight, it's portable even via air. And this would significantly increase the reaction time for the actions that are far away. You can also attach it to the truck. It's a really easy solution, and for small distances, this is really fast option. But if we start talking about longer distances, then it makes sense to put it on a trailer, so you will be reaching the accident site faster. So here you can see a video of the Hydra in action in real life. So now we're going to look a bit into experience and use cases that may come up. So for the firefighters, the overall bigger concerns are that the environment where they need to work is rapidly and structure is new, and there may be some new danger zones that people are not aware of. They are yes. So also a different type of gas tanks, especially mobile ones. From time to time, it happens that there will be an accident, and it can become a disaster really easily when we're not able to get close enough. Also, as I mentioned before, the military polygons with unexpected ordinances. In the summertime, the spark is really easy to happen, and big field fires can come out from that. So it's really important to mitigate and act fast on those occasions. So it will be very useful for the unmanned vehicles with low ground pressure to extinguish those situations as fast as possible. Also related to the previous one, in a dry season, there are small parks can become disastrous in the forest area, and there is a lot of manpower needed and the resources to mitigate those. For example, UGVs could really easily help building the hose networks on a difficult terrain, and it will speed up the whole process a lot. And also, last point, the hard and limited accessibility areas like railroads, narrow streets would be perfect place to ease and reduce these response times with unmanned systems by either carrying more equipment closer faster or getting the water lines and fire monitors closer to the primary source of the fire. Now we're going to be looking into one of the most important aspects of the vehicle are the danger zones, because it's the most likely the biggest benefit that one robot can bring you is that you can enter the danger zone without putting any humans at risk. So due to the remotely controllable, the operator can operate the vehicle from safe distance and respond to the situation according to sensors feedback. And it's very hard to assess the danger zone's dimensions accurately from far away. So sensors of the robots could be used to confirm or deny all that kind of information in the scene of incidents. And when we add a other layer of capabilities like fire monitor on top of UGV, we can decrease the reaction time from getting the intelligence in, and then we can just react on exactly the same time based on that information. And actually, a example from Estonia, there was one hardware in Estonia that there was a fire. It was initially reported that there's about 30-ton acetone tank out of metal at the fire that is burning. But Themis was sent to conduct a reconnaissance on that objective. But the Reka was not able to do that from air because the building had partially collapsed So it was really critical to do that from the ground. So they used the UGV's main cameras to provide the information and actual picture feedback. And what they recognized is that that container actually was out of plastic and it had already melted. So they took that information into account, and actually they could increase the danger zone by double. Another perfect case where to use this kind of technology would be in chemical factories. For example, this is in Netherlands, and using robots to access and identify causes of this type in this type of environment would definitely be able to get closer and be more effective than sending firefighters into that kind of danger zone where there is so many unexpected explosions and stuff can happen. And also one example from Estonia, there was a gas tank explosion and other gas tank got ignited as well. So the firefighters were not able to get closer to the high chance of another explosion. So and there was an additional 40 tons of fuels laying around close. So for events like this, unmanned vehicles would be a tool to cool down areas. For example, just to prevent that to prevent it getting even bigger of a disaster than it is already. Here is also another use case that's when was used in Estonia when they transported 200 kilogram airplane bombs from extraction site to the demo site, and they drove it remotely in a convoy for several kilometers, and it enabled the safe handling and transportation of this munition. Also, another place in Europe, we have old towns which are really narrow streets, and it's hard to operate there with standard fire trucks. So robotics could be a really good assistance over there as well. And also another big place where things happen is fire tunnels, tunnel fires, and underground garages. For one example from Switzerland. Like one mile from the exit, there was a car accident and it got filled with smoke and it had numerous casualties. So in this situation, UGVs could be used to get big, ventilators, or even just keep the temperature down and send the vehicle in there just to get access of the real feedback from the accident and get better intelligence, and then the firefighters are able to react better to this scene. And also last use case would be a disaster relief scenario where mainly usually there's a lot of UGVs could help take a big load of equipment closer, for example, in the disaster site, because the resources in that kind of areas are always, and the UGV is a perfect choice because you will have one vehicle for several functions actually, and you could do a lot more than just transport the goods. And this is actually how we provide the innovative robotic solutions for challenging environments. And I would really like to thank Baltic Fire Forum for this opportunity, for letting us to participate, and hopefully we were able to add some value to this event. And thanks for listening. And also I would like to share you with some of the places you can follow us. We have LinkedIn, Facebook, YouTube pages, homepage. If you have any questions, remarks, and you want to know something more about our products and the way we challenge those environments, you can contact me. My email is remo.at.com. And yeah, thank you for listening, and bye.
Thank you very much, Remo. Very interesting topic. Now we can see that, robotics is really, really wild, I would say. Very broad area of using this. So now I really believe that, It's I think I saw it also disinfecting the air. I'm not sure, but I think it was the COVID-19 thing that in the premises where people could not enter, they just went into the robot itself and they sprayed all this anti-COVID vaccines and so on and so on. So robots are really, I thought it's a future. It's a reality, and it's nowadays. Truly. And I'm really glad that we have this producer not somewhere away, United States or China. We have it here in Estonia. So this is really, really good, nice thing to hear. That Baltics are, also leaders in robotics, not only IT and fast internet. So our first day of second edition of Baltic Fire Forum is coming to an end. We had really tremendous topics about tactical ventilation from firefighting guru Shimon. We discussed it. Really good one. We had Kamil Marianek with foam as a super effective extinguishing agent. We had Holland, Martin Bosman with virtual reality and this broadness of how much can we educate and train in this virtual reality thing. And Remo Oeste, I mean, Estonia, wow, a huge applause, really for all those robotic novatories. So what about you, Simonas? I'm a bit exhausted, but really happy.
I'm truly, really happy, Martinas. It's a truly wonderful day. I'm really happy to be here, and I was waiting for that conference. I'm waiting already for next year conference.
Well, we had to postpone it because it was not, in the reality. We had to go online. But nevertheless, of the presentations which we heard today, it's really wow. And I say I'm really looking forward to tomorrow. Will you join me, Simonas? Because I really enjoyed your.
Oh, really, Matthias. I will enjoy you and truly waiting for that. Yes.
Okay. So thank you, Simonas. Thank you very much, dear viewers. I will wait for you tomorrow. Tomorrow at 10 o'clock, we shall do the next stage, the next day of second edition of Baltic Fire Forum. So see you tomorrow.